Look up at the night sky, at the glittering tapestry of stars, and you might think you're seeing the universe in its entirety. You see the majestic swirl of the Andromeda Galaxy, the brilliant clusters of the Milky Way, the familiar constellations that have guided humanity for millennia. But what if I told you that everything your eyes can perceive, every star, every planet, every brilliant nebula, is nothing more than the glittering decoration on an invisible scaffold? What you are actually looking at is the ghostly illumination cast upon a far greater, hidden structure, a structure made of a substance so mysterious, it defies everything we think we know about reality. This is the realm of dark matter, and the colossal, invisible cocoons it forms are the true architects of our cosmos, the cosmic dark matter halos. These are not mere clouds of odd particles. They are the gravitational skeletons upon which galaxies are built, the unseen hands that have sculpted the universe from the beginning of time. We are living in a universe dominated by a shadow, and today we are going to pull back the curtain. The story of dark matter is perhaps the greatest detective story in all of science. For nearly a century, astronomers have been gathering clues, piecing together evidence for something they cannot see, touch, or directly measure. It started with the frantic spins of galaxies, rotating so fast that they should tear themselves apart, held together by a gravitational glue that was completely invisible. It continued with the bending of light around massive galaxy clusters, warping the fabric of space-time with a strength that far exceeded the pull of the visible stars. The conclusion became inescapable. The universe we see is just a small fraction of the universe that is. Over 80% of all the matter in the cosmos is this dark, elusive substance, and its primary manifestation is in these vast, sprawling halos that can stretch for millions of light years. Imagine a single, invisible sphere, so immense that our entire Milky Way galaxy, with its hundreds of billions of stars, is just a small, bright trinket suspended at its very center. That is the scale of the mystery we are dealing with. This journey we are about to embark on is not just a list of facts, it is an expedition into the deepest unknowns. We will explore 25 specific, mind-bending mysteries that these cosmic dark matter halos present. We will confront questions that challenge the very foundations of physics. What exactly is this stuff made of? Are we dealing with unknown particles, or could it be that our understanding of gravity itself is fundamentally flawed? Why do these halos have such strange, unexpected shapes, with their inner densities appearing smoother than our theories predict? How do they dictate the fate of galaxies, acting as cosmic puppeteers over billions of years? Each mystery we uncover will pull us deeper into a narrative of cosmic proportions, a story where the answers we find only lead to more profound and thrilling questions. So prepare to have your perception of reality shifted as we begin our investigation into the 25 mysteries of the cosmic dark matter halo. And so we arrive at the very first and arguably the most profound mystery on our list. What exactly is this shadowy substance? We have overwhelming evidence that it exists, that its gravitational pull is the dominant force shaping the cosmos, yet its fundamental identity remains utterly unknown. It's like knowing a powerful, invisible giant is living in your house because you can see the furniture moving, but you have no idea what the giant looks like, what it's made of, or even if it's a single entity or an entire family of giants. For decades, the leading hypothesis has pointed toward a new, exotic kind of particle. The most famous candidate is known as a WIMP, which stands for Weakly Interacting Massive Particle. The name itself tells a story. These particles would have significant mass, explaining their strong gravitational influence, but they would interact with normal matter only through the weak nuclear force and gravity, making them incredibly difficult to detect. It's a beautifully elegant idea, and for years, physicists built incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the faintest bump of a WIMP passing through. Yet, despite monumental efforts, these detectors have remained silent. The WIMP, if they are out there, are even more elusive than we imagined. This silence has forced physicists to broaden the search. Another compelling candidate is the action, a hypothetical particle that is incredibly light but would exist in astronomical numbers, like a faint cosmic mist permeating every corner of space. Unlike WIMP, actions were originally proposed to solve a completely different problem in particle physics, but they happen to have the perfect properties to be dark matter. They would barely interact with light or matter, yet their collective mass could account for the missing gravity. The search for actions is like trying to tune a radio to a station that has never broadcast before, using equipment of unimaginable sensitivity. The challenge is that the properties of these particles, their mass, their interaction strength, are completely unknown. We are essentially searching for a needle in a universe-sized haystack without being entirely sure what the needle looks like. Faced with the stubborn elusiveness of particle dark matter, some scientists have proposed a radically different solution. What if there is no mysterious particle at all? What if instead our understanding of gravity is incomplete? This idea is known as modified Newtonian dynamics, or MND. It suggests that on the vast galactic scales, gravity behaves differently than Isaac Newton or Albert Einstein predicted. Under MND rules, the force of gravity doesn't weaken as quickly with distance as we think, which could explain why stars on the outer edges of galaxies rotate so quickly without needing any extra invisible matter. It's an audacious proposal to rewrite the laws of physics rather than invent a new substance. And while MND can successfully explain the rotation of some individual galaxies, it struggles mightily with other evidence. It has a very difficult time accounting for the way massive galaxy clusters bend light, a phenomenon called gravitational lensing, which clearly points to there being far more mass present than we can see. Most compellingly, when we observe galaxies colliding, we can sometimes see that the gravitational mass and the visible mass become separated, with the gravity leading the way. This is almost impossible for MND to explain, but it makes perfect sense if dark matter is a substance that can flow through itself and normal matter without friction. So the mystery deepens. Are we missing a particle, or are we missing a deeper law of gravity? The answer will redefine our place in the universe. This conflict between the grand predictions of our supercomputer simulations and the stubborn evidence from real-world observations leads us directly to our second great mystery, a puzzle so persistent it has earned its own name, the cusp core problem. Think of it as a cosmic architectural flaw, a disagreement between the blueprint and the finished building. According to our most sophisticated models of how dark matter should behave under the influence of gravity alone, a dark matter halo should have a very specific shape. Its density should be greatest at the very center, rising sharply and steeply in what physicists call a cusp. Picture a perfectly smooth, steep-sided mountain, like Mount Fuji, where the slope becomes increasingly intense as you approach the summit. That's what our simulations, which treat dark matter as cold and collisionless, consistently produce. The gravitational collapse over billions of years naturally sculpts these dense, sharp peaks at the heart of galaxies. But when astronomers train their telescopes on small, faint dwarf galaxies, the very galaxies that are supposed to be dominated by dark matter, and thus perfect laboratories for studying it, they find something entirely different. Instead of a steep mountain peak, the data suggests a gentle, rolling hill. The dark matter density in the center of these galaxies appears to be almost constant, forming a flat core. It's as if someone came along and took the sharp tip off the mountain, leaving behind a wide, level plateau. This isn't a minor discrepancy, it's a fundamental failure of our predictions on the smallest galactic scales. If our understanding of dark matter is correct, why don't we see these predicted cusps where they should be most obvious? One compelling line of thought suggests that the problem may not lie with dark matter itself, but with something we can see, ordinary matter. Specifically, the violent cyclical activity of stars. The core-cusp problem is most evident in dwarf galaxies, which have relatively shallow gravitational wells. In their early history, these galaxies would have formed massive stars that lived fast and died young, exploding as supernova. These colossal explosions blast enormous amounts of gas and energy outwards, dramatically changing the gravitational landscape of the galaxy's center. As this normal matter is pushed and pulled by these stellar winds and explosions, its gravity interacts with the dark matter. Some theorists propose that this rhythmic pumping action effectively heats up the dark matter, scattering it and smoothing out the sharp central cusp into a flatter core over billions of years. It's a fascinating idea that the brilliant, short-lived fireworks of stars could be the sculpting tool that reshapes the invisible dark matter skeleton of their galaxy. However, if this stellar feedback explanation proves insufficient, the cusp core problem points toward something even more revolutionary. That dark matter might have properties beyond what we've assumed. Perhaps dark matter isn't completely dark to itself. What if dark matter particles can interact with each other through some unknown force, a dark version of electromagnetism? These self-interactions could cause the particles to collide and bounce off one another in the crowded galactic center, effectively transferring energy from the inner, denser regions to the outer areas. This process would naturally erase the sharp cusp, creating the smooth core we observe. Alternatively, dark matter could be warm rather than cold, meaning the particles were moving at a significant fraction of the speed of light in the early universe. This frenetic motion would have prevented them from clumping together on the smallest scales, naturally suppressing the formation of those dense central peaks. The cusp core problem, therefore, is far more than a technical disagreement. It is a critical testing ground. It forces us to ask whether we need to add complex astrophysics to our models, or whether we need to fundamentally rethink the intrinsic nature of the dark universe itself. This growing tension between our theoretical expectations and the actual galactic landscape brings us to our third enigma, a paradox with a name that almost sounds like a taunt: the too big to fail problem. The phrase itself is borrowed from the world of finance, describing banks so large and interconnected that their failure would be catastrophic to the entire system, making governments obligated to bail them out. But in the context of dark matter, it describes something just as startling: gigantic, seemingly failed galaxies. Our most powerful computer simulations of cosmic evolution paint a very specific picture of what our own Milky Way's dark matter halo should look like. They tell us that our galaxy is not alone in its vast, invisible cocoon. It should be surrounded by a swarm of smaller dark matter clumps called subhalos. These are the leftover building blocks from the galaxy's formation, captured by its immense gravity. And according to the models, the largest and most massive of these subhalos should be enormous, with such strong gravitational pulls that they simply should not have failed to form stars. They possessed all the ingredients for success: copious amounts of dark matter to gather gas and a deep gravitational well to hold it. They were, in a cosmic sense, too big to fail. Yet, when we peer out at the Milky Way's neighborhood, the story we observe is dramatically different. We do see a collection of small satellite galaxies, like the Large and Small Magellanic Clouds, orbiting our own. But there is a glaring mismatch. Our simulations predict that we should be accompanied by roughly 10 of these colossal subhalos, each so massive that it should have given birth to a bright, bustling dwarf galaxy, easily visible to our telescopes. But we only see a handful of much smaller, fainter satellites. The most massive predicted subhalos appear to be completely dark, ghostly structures of pure dark matter sailing through the void without a single star to illuminate them. It's as if we predicted a bustling metropolis would have 10 major suburbs, but when we look, we only find 3 small villages and 7 empty, perfectly prepared building sites. The question is unavoidable. Where did all the stars go? Scientists have pursued several compelling avenues to solve this cosmic ghost town mystery. One possibility is that our simulations, while incredibly sophisticated, might still be missing a key piece of astrophysical physics. Perhaps the process of star formation in these massive subhalos was stifled by an external force. A leading theory points to the harsh environment of the early universe. Before galaxies settled into their current majestic forms, the cosmos was flooded with intense ultraviolet radiation from the first generations of stars and quasars. This radiation could have heated the hydrogen gas within these large subhalos, preventing it from cooling down, collapsing, and eventually igniting into stars. It's like trying to build a fire in a strong wind. The fuel is there, but the conditions prevent it from ever catching alight. In this scenario, these subhalos were indeed too big to fail in terms of their dark matter content, but they were born at the wrong time and place, subjected to a cosmic sterilization that left them permanently dark. Another fascinating angle considers the nature of dark matter itself, revisiting the idea of warm dark matter. If dark matter particles were slightly warmer, meaning they had more intrinsic motion in the early universe, it would have a direct effect on the formation of these smallest structures. Warm dark matter would smooth out the cosmic landscape on small scales, suppressing the formation of the very tiniest subhalos. This could potentially solve the problem by lowering the predicted number of massive satellites, bringing the simulation more in line with what we actually observe. However, this solution walks a fine line. If the dark matter is too warm, it might suppress too much structure, creating a new set of conflicts with other observations. The too big to fail problem, therefore, acts like a precise scale, carefully weighing the competing ideas of cold versus warm dark matter and challenging us to find the perfect balance that explains the galaxy we live in versus the one our computers simulate. Building directly on the ghostly suburbs of the too big to fail problem, we encounter an even more pervasive and numerical puzzle, the missing satellites problem. This mystery highlights a staggering discrepancy between the grand architecture predicted by our leading cosmological model, known as lambda cold dark matter, and the comparatively empty cosmic neighborhood we actually observe. The mathematics of gravitational collapse are powerful and clear. As the universe evolved from a nearly smooth soup of matter after the Big Bang, dark matter, being the dominant component, should have clumped together first. It formed a cosmic web of filaments, and at the intersections of these filaments, the largest halos, like the one hosting our Milky Way, coalesced, but crucially, this process is hierarchical. A vast hierarchy of smaller clumps or subhalos should have also formed independently, only to later be captured by the gravity of a larger neighbor. Our most detailed simulations show this process in stunning detail. They predict that a galaxy like ours should be surrounded by a swirling retinue of thousands of these dark matter subhalos. They range in size from enormous structures, which we already discussed in the too big to fail context, down to countless trillions of smaller clumps, some no more massive than a single star. The expectation was straightforward. Where you have a significant lump of dark matter, its gravity will pull in ordinary gas. That gas will cool, condense, and eventually ignite into stars, birthing a visible dwarf galaxy. So, if the simulations say there should be thousands of dark matter clumps orbiting the Milky Way, logic suggests we should see thousands of small, faint satellite galaxies accompanying us. Yet, when astronomers conduct painstaking surveys of our galactic backyard, they only confidently identify several dozen. The numbers are devastatingly lopsided, thousands predicted, only dozens observed. It's as if we predicted a vast archipelago of islands surrounding a continent, but when we set sail, we only find a handful, with the rest of the ocean appearing utterly empty. This glaring absence forces us to consider two broad possibilities. The first is that our understanding of astrophysics, the behavior of normal matter, is incomplete. Perhaps the process of galaxy formation is far more inefficient than we thought, especially on the very smallest scales. The smallest dark matter subhalos have very shallow gravitational wells. While they can pull gas in, holding onto it is another matter entirely. In the violent early universe, two key phenomena could have prevented these tiny halos from ever forming stars. The first is cosmic reionization. A few 100 million years after the Big Bang, the first stars and galaxies switched on, flooding the universe with intense ultraviolet radiation. This radiation heated the hydrogen gas throughout space, making it too energetic to collapse into the feeble gravitational grasp of the smallest subhalos. It effectively sterilized them, stripping away their potential to ever become galaxies. Think of it like trying to fill a shallow puddle during a hot, windy day. The water evaporates almost as soon as it lands. The second astrophysical hurdle involves supernova feedback. Even in those small halos that manage to gather some gas and form a first generation of stars, the aftermath could be catastrophic. Massive stars die in spectacular supernova explosions. In a large galaxy like the Milky Way, the gravity is strong enough to withstand this violence and even recycle the ejected material. But in a tiny dwarf galaxy, the energy from just a few supernova could be enough to blow all the remaining gas clean out of the halo, permanently halting any further star formation. It's a tragic case of a young system essentially committing suicide, its own brilliant fireworks destroying its future. So, in this view, the thousands of subhalos are indeed out there, but they are dark, barren, and silent, their potential for light extinguished billions of years ago. The second, more radical possibility is that the problem lies not with the gas, but with the dark matter itself. The lambda-CDM model assumes dark matter is cold, meaning its particles moved slowly in the early universe, allowing it to clump readily on all scales, down to the very smallest. But what if dark matter is slightly warm? Warm dark matter particles would have zipped around at higher speeds early on, which has a smoothing effect. This extra motion would wipe out the formation of the very smallest clumps, like a cosmic iron erasing the finest wrinkles from the fabric of space. A warm dark matter universe would naturally predict far fewer small subhalos, potentially bringing the predicted numbers much closer to the dozens we observe. However, this is not a perfect fix. If the dark matter is too warm, it might also erase structures we know do exist, creating new tensions with other observations. The hunt for these missing satellites, therefore, is really a hunt for the fundamental properties of the dark universe, a desperate search for ghostly islands that may hold the key to understanding the invisible ocean in which we float. Just when we think we have a handle on the grand architecture of our cosmic neighborhood, the universe presents us with a pattern so precise and so unexpected that it seems to defy the very randomness we expect from gravity's chaotic dance. This brings us to our fifth mystery, the baffling planes of satellites. Imagine for a moment that you could see the dark matter subhalos surrounding our Milky Way. According to our best models, which treat dark matter as a collisionless fluid governed solely by gravity, you would expect to see a vast spherical swarm. These subhalos and the dwarf galaxies they may host should orbit in every conceivable direction, like a chaotic cloud of bees buzzing around a hive. There should be no preferred orientation, no grand design, just a statistically random distribution that reflects the isotropic pull of the galaxy's gravity. But that is not what we see, not at all. When astronomers meticulously map the positions and motions of the dwarf galaxies orbiting the Milky Way, a startling pattern emerges. Instead of a spherical cloud, a significant number of these satellites appear to be arranged in an incredibly thin, vast disk. They are not just roughly in the same area, they are aligned along a single, narrow plane that slices through our galaxy. Even more astonishingly, many of these dwarfs within this plane are not just moving randomly. They appear to be coherently streaming in the same direction, like cars on a cosmic freeway, suggesting the entire structure might be rotating. This is not a subtle effect. It's a stark, geometric arrangement that looks profoundly unnatural within the standard model of galaxy formation. The plot thickens immensely when we look at our nearest large galactic neighbor, the Andromeda Galaxy. Astronomers observing its satellite system have found an even more dramatic and pronounced version of the same phenomenon. Andromeda's dwarf galaxies are also organized into a vast, rotating plane, one that is even thinner and more structured than our own. The probability of this happening by pure chance in both of the two largest galaxies in our local group is astronomically low. It's as if you tossed a handful of confetti into the air 100 times, and twice it landed perfectly arranged to spell your name. This coincidence is so striking that it screams for an explanation beyond simple luck. These planes of satellites present a direct challenge, suggesting that our simulations are missing a crucial ingredient, either in the physics of dark matter or in the complex process of how galaxies assemble. One school of thought seeks an explanation within the known laws of physics, focusing on the dynamics of galaxy formation itself. Perhaps these planes are a temporary cosmic fossil, a relic of a specific event in the past. A leading hypothesis suggests they could be remnants of a group of small galaxies that fell into the Milky Way or Andromeda together in a single, massive accretion event. If a dozen dwarf galaxies were all part of one larger group that was captured by our galaxy's gravity billions of years ago, they would have entered on similar trajectories. Their shared origin could have preserved their aligned motions, creating the coherent plane we see today. Over many more billions of years, gravitational tugs from the main galaxy and from each other should eventually randomize their orbits, dissolving the plane. So perhaps we are just living at a special time, lucky enough to witness this elegant structure before it fades away. However, the sheer thinness and coherence of the planes, especially around Andromeda, push the limits of this tidal debris explanation, making some scientists wonder if a more fundamental force is at work. This leads to a more radical possibility that the planes of satellites are a signature of the very nature of dark matter. The standard cold dark matter model has been spectacularly successful on the largest scales, but its assumption that dark matter interacts only through gravity may be its downfall on these smaller galactic scales. What if dark matter can interact with itself through a non-gravitational force? This concept, known as self-interacting dark matter, could provide a mechanism to create these vast disks. In the early universe, as the massive dark matter halo of a galaxy like the Milky Way was collapsing, self-interactions between dark matter particles could have caused them to lose energy and settle into a rotating disk, much like how normal gas collapses to form the visible disk of a spiral galaxy. The dwarf galaxy subhalos would then form within this pre-existing dark matter disk, naturally inheriting its flat, rotating structure. This would be a profound revelation, implying that the dark sector of the universe has a rich and complex physics of its own, complete with forces and interactions we are only beginning to imagine. The planes of satellites stand as one of the most visually compelling mysteries in modern cosmology. They are a pattern etched into the sky that our most powerful theories struggle to explain. Whether they are a clue to a forgotten chapter in our galaxy's violent history or a direct glimpse into the hidden properties of the universe's dominant matter, they remind us that the cosmos is far more ordered and far more strange than our simulations often predict. This organized structure in the chaos of space forces us to look closer, to question our assumptions, and to consider that the invisible framework of the universe may be woven with threads we have not yet begun to see. Moving from the large-scale architecture of satellite planes, we zoom into the very dynamics of individual galaxies, where another profound puzzle awaits. If dark matter halos are the universal gravitational foundation, you might expect galaxies that look similar in terms of their stars and gas to behave in similar ways. But the universe, it seems, delights in complexity. This brings us to the enigma of the diversity of rotation curves. A rotation curve is essentially a graph that plots the orbital speed of stars and gas against their distance from the center of a galaxy. According to basic Newtonian gravity, stars on the outer edges, farther from the central mass, should orbit more slowly, just as Pluto moves much more sluggishly around the Sun than Mercury does. For decades, we've known that galaxies don't obey this simple rule. Their rotation curves are flat, meaning stars on the outskirts orbit just as fast as those near the center, providing the original, classic evidence for dark matter. The invisible halo provides the extra gravitational pull to keep these stars whipping around. The mystery, however, has deepened when astronomers began comparing rotation curves of galaxies that, by all accounts, should be twins galaxies with nearly identical masses, sizes, and amounts of visible matter. They found something startling. Their rotation curves were not identical. In fact, they could be wildly different. Some galaxies showed the expected strong signature of a dense dark matter halo, with speeds remaining high far out into the void. Others, their apparent twins, showed rotation curves that declined much more steeply, suggesting a surprisingly feeble dark matter presence. It's as if you examined two houses that were built from the same blueprint, with the same number of rooms and the same building materials, but when you tested their foundations, one was anchored deep into solid bedrock while the other was perched precariously on sand. This diversity is a major puzzle. If the amount of normal matter is the same and the laws of physics are the same, why is the inferred dark matter content so different? This discrepancy forces us to look beyond a simple, static picture of dark matter halos and consider the dynamic, often violent, life story of a galaxy. A galaxy's rotation curve may not be a snapshot of a fixed structure, but a living fossil recording billions of years of cosmic history. The key may lie in the interactions a galaxy has endured. Imagine two similar galaxies forming in the early universe. One leads a relatively quiet, isolated life, steadily accumulating gas and forming stars in a predictable way. Its dark matter halo remains relatively pristine, undisturbed. The other galaxy, however, might have a much more eventful history. It could have undergone major mergers with other galaxies or experienced intense, sustained bursts of star formation. These energetic events don't just affect the visible stars and gas, they can profoundly reshape the invisible dark matter halo itself. The process likely involves gravitational feedback between the normal matter and the dark matter. During a period of intense star formation, the colossal energy from supernova explosions can push and pull on the surrounding gas. This rhythmic pumping action over cosmic timescales can transfer energy to the dark matter particles at the galaxy's center. Think of it like stirring a cup of coffee with a spoon. The swirling motion of the liquid, the normal matter, gradually alters the distribution of the grounds, the dark matter, at the bottom of the cup. This gravitational stirring can cause the dark matter to drift outward, effectively puffing up the inner part of the halo and making it less dense. For a galaxy that has experienced such a turbulent past, the resulting rotation curve would show a slower rise and a weaker overall signature, precisely because its dark matter has been dynamically heated and redistributed. An even more dramatic mechanism involves close encounters with other galaxies. If a galaxy passes near a massive neighbor, the immense tidal forces can act like a cosmic comb, stripping away significant portions of its outer dark matter halo. This tidal stripping would leave the galaxy with a much less massive, and therefore less gravitationally potent, dark matter component. Its rotation curve would subsequently appear anemic compared to an isolated counterpart. This diversity tells us that the relationship between a galaxy and its dark matter halo is not a simple one-to-one mapping. It is a complex dialogue, a dance between the visible and invisible worlds where the history of collisions, bursts of stellar activity, and near misses all leave an indelible mark on the galactic fingerprint. The rotation curve is not just a measure of mass, it is a biography written in the language of gravity, and we are only just learning how to read its most surprising chapters. But if the history of a galaxy can reshape its dark matter halo, then we must confront the powerful engine behind that change, the ordinary matter itself. This brings us to the heart of our seventh mystery, a process known as baryonic feedback. For a long time, cosmologists treated galaxies as relatively simple systems, a halo of dark matter that provides the gravitational anchor and a clump of normal matter, stars, gas, and planets, that simply sits inside it, following the gravitational rules set by the invisible host. It was a picture of a passive passenger carried by an invisible vehicle, but we are now realizing this relationship is anything but passive. The visible components of a galaxy are not just inert cargo, they are active, often violent agents that can push back against their dark matter foundation, reshaping the very gravitational landscape they inhabit. The term baryonic feedback might sound technical, but the concept is a dramatic one. Baryons is the scientific name for the particles that make up the familiar world: protons and neutrons, the building blocks of stars, planets, and us. Feedback describes a loop of cause and effect. In a galaxy, enormous amounts of energy are released by two primary sources: the spectacular deaths of massive stars in supernova explosions, and the voracious appetites of supermassive black holes at galactic centers, known as active galactic nuclei. This energy doesn't just vanish, it floods into the surrounding galaxy, heating gas, driving powerful winds, and creating intense pressure. This baryonic activity then feeds back into the system, altering the conditions that led to it in the first place. And crucially, this feedback doesn't just affect the visible gas. Its gravitational repercussions can actually rearrange the invisible dark matter. To understand how, let's consider a simplified analogy. Imagine a large, tranquil swimming pool representing a galaxy's dark matter halo. Now drop a powerful motorized toy boat into the center. This is the bustling, energetic disk of stars and gas. As the boat's propeller churns the water, it creates waves and currents that radiate outward. Initially, the water close to the boat is thrown into chaos, but over time, the persistent churning can set up larger, more persistent circulation patterns throughout the entire pool. The boat's activity has fundamentally changed the water's distribution and motion. In a galaxy, supernova and black holes are like not one, but millions of propellers churning simultaneously. The energy they release creates waves of pressure that push on the surrounding gas. As this normal matter is sloshed around, its changing gravitational pull interacts with the dark matter particles. This gravitational coupling can slowly transfer energy from the frantic baryons to the passive dark matter, effectively heating it up and causing it to move outward from the galactic center. This process can smooth out the predicted dense cusps in dark matter halos, potentially solving the cusp core problem we discussed earlier, but it also introduces a layer of tremendous complexity. The most dramatic form of feedback comes from active galactic nuclei. At the heart of most large galaxies, including our own Milky Way, lies a supermassive black hole, weighing millions or even billions of times the mass of our Sun. When these monsters are actively feeding on surrounding gas, they become the most powerful engines in the universe, emitting vast jets of radiation and particle winds that can outshine the entire galaxy. This outpouring of energy can be so immense that it pushes the surrounding gas far out into the halo, effectively shutting down star formation across the galaxy in a phenomenon called quenching. But the effect goes even further. By violently displacing such a huge amount of normal matter, the black hole's feedback alters the gravitational potential of the entire central region. The dark matter, which was in a delicate balance with the gravity of the central stars and gas, must respond. It can either contract further or expand, but in many cases, the removal of the central mass causes the dark matter halo to slightly puff up, becoming less concentrated. This means that the growth of a galaxy and the growth of its central black hole are intrinsically linked, not just by coincidence, but by a direct mechanical feedback loop that governs the evolution of both the visible and invisible components. This realization fundamentally blurs the line between the dark and light sides of a galaxy. We can no longer cleanly separate the two. The distribution of dark matter is not just a relic of the Big Bang. It is a living record sculpted by the fiery lives and deaths of stars and the awesome power of central black holes. This makes the task of understanding dark matter vastly more difficult. When we observe a galaxy with a strangely shaped rotation curve or a missing central cusp, we now have to ask, is this a signature of dark matter's intrinsic properties, or is it the aftermath of billions of years of baryonic feedback? It becomes a cosmic detective story where the clues have been overwritten by subsequent events. Disentangling these effects is one of the greatest challenges in modern astrophysics, requiring incredibly sophisticated computer simulations that model not only the gravity of dark matter, but also the complex physics of gas, radiation, and magnetic fields. The mystery of baryonic feedback forces us to see galaxies not as static islands in space, but as dynamic, evolving ecosystems, where the visible and the invisible are locked in a continuous gravitational dance. Yet another class of cosmic object forces us to question our most basic assumptions about how galaxies come to be, presenting a paradox that seems to defy logic. We now arrive at the mystery of the ultra-diffuse galaxies, or UDGS. Imagine finding, in a vast field of brilliant spiral and elliptical galaxies, a ghost. An object that has the sheer physical size of our own Milky Way, spanning tens of thousands of light years, but one that is so utterly faint it is almost transparent. If you were to point a small telescope at it, you would see nothing at all. It is only with the most powerful observatories, using painstakingly long exposures, that these spectral forms reveal themselves, not as blazing cities of stars, but as faint, wispy smudges of light. They are the cosmic equivalent of a balloon inflated to the size of a beach ball, but containing only a single, faint breath of air. The premier example of this enigma is a galaxy known as Dragonfly 44, located in the distant Coma cluster. The mystery of Dragonfly 44 and its kin is twofold. First, how did a dark matter halo massive enough to support a galaxy the size of the Milky Way end up with so few stars? Under our standard model of galaxy formation, a halo of that immense size and gravitational power should have been a superstar, a prolific factory for stellar formation. It had more than enough gravitational pull to gather vast reservoirs of hydrogen gas and compress it into billions upon billions of suns, and yet it failed. Spectacularly, the number of stars in Dragonfly 44 is less than 1% of the stars in our Milky Way, scattered so sparsely across its enormous volume that it is barely a galaxy at all. It's as if a construction crew was given all the materials and the blueprint to build a skyscraper, but only ever managed to erect a few small sheds on the massive foundation. The second related puzzle is that these galaxies are, paradoxically, incredibly effective at hiding their dark matter content. Because they have so few stars, it is extremely difficult to measure their masses using the standard technique of tracing stellar motions. Their ghostly nature makes them perfect dark matter cloaking devices. Scientists have proposed several compelling scenarios to explain the existence of these failed giants. One leading theory places the blame on the galaxy's environment. Ultra-diffuse galaxies are often found within dense galaxy clusters like the Coma cluster, which are chaotic and violent places. In this scenario, a normal dwarf galaxy, rich with gas, falls into the cluster for the first time. As it plows through the incredibly hot, thin plasma that fills the space between galaxies in the cluster, a material known as the intracluster medium, it experiences a dramatic stripping effect. The pressure of this plasma acts like a powerful cosmic wind, blowing the galaxy's gas away before it can form new stars, At the same time, the gravitational tides from the cluster's immense mass can stretch the galaxy, puffing it up and making it appear larger and more diffuse. In this view, an ultra-diffuse galaxy is not a primordial failure, but a victim of cosmic circumstance, its stellar potential ripped away by a hostile environment. However, the environmental explanation doesn't fit every case. Astronomers have since discovered ultra-diffuse galaxies living in quiet, isolated voids, far from the punishing conditions of clusters. This suggests that some of these ghosts are born that way, their fate sealed by internal processes. Perhaps their dark matter halos assembled unusually late, after the epoch of peak star formation had already passed. Or maybe their gas was heated and prevented from cooling by the faint, pervasive ultraviolet background radiation that filled the early universe, a process we touched on with the missing satellites. Another fascinating internal mechanism involves particularly potent stellar feedback. In a small galaxy, if the first waves of star formation are just a little too efficient, the resulting supernova could blow out nearly all of the remaining gas in a single catastrophic event. Without gas, star formation stops forever, leaving behind a massive dark matter halo populated by only that first, faint generation of stars, which then slowly drift apart over billions of years to create the diffuse appearance we see today. The existence of ultra-diffuse galaxies like Dragonfly 44 is a stark reminder that galaxy formation is not a simple, deterministic process. It is a complex interplay between the inherent properties of the dark matter halo and the often unforgiving lessons of a galaxy's life story, where it was born, what violence it endured, and how its own internal fires shaped its destiny. These ghostly giants challenge the very definition of a galaxy and force us to consider that the universe has more than one way to build or fail to build upon its invisible dark matter foundations. Following the enigma of the ghostly ultra-diffuse galaxies, we are led to an even more extreme and elusive concept, the idea of dark matter halos that are completely barren. This is our ninth mystery: dark halos without a single star, a single wisp of gas, or any luminous structure whatsoever. These would be the universe's ultimate phantoms, vast gravitational islands of pure dark matter sailing through the cosmic void in absolute darkness. If ultra-diffuse galaxies are failed constructions, then these dark halos would be construction sites where the building never even began. The profound implication is that there might be a minimum threshold of mass or a specific set of conditions required for a dark matter halo to successfully attract and retain the ordinary matter needed to birth a galaxy. Finding these pure dark halos would be like discovering the invisible foundations of cities that were never built, revealing the bare bones of cosmic structure itself. The primary tool for hunting these invisible giants is one of astronomy's most powerful techniques, gravitational lensing. As we've discussed, massive objects warp the fabric of space-time around them, bending the path of light for more distant background galaxies. This creates telltale distortions, stretched arcs, and multiple images that act as a perfect scale for weighing the foreground object, regardless of whether it emits any light. The hunt for dark halos, therefore, involves scanning the sky for these characteristic warps and twists in the light of distant galaxies, but finding no visible source for the gravity that is causing them. It's like seeing the ripples on a pond's surface, indicating that something has fallen in, but when you look, the water is completely clear. Astronomers have indeed found several tantalizing candidates. There are instances where the pattern of gravitational lensing suggests a significant concentration of mass, a clear gravitational signature, yet when they point their most sensitive telescopes at that exact spot, they see nothing. No galaxy, no cluster, just empty space. These empty field lenses are some of the most compelling, albeit controversial, pieces of evidence for the existence of pure dark halos. However, confirming these candidates is incredibly challenging. The main difficulty lies in definitively ruling out every other possibility. Could the lensing signal be produced by a very faint, distant galaxy that is simply too dim for our current telescopes to detect? Perhaps it's caused by the collective, uneven pull of several smaller structures along the line of sight, rather than one single massive halo. To claim a definitive discovery of a dark halo, astronomers must eliminate these other explanations with a very high degree of confidence, which requires exquisitely deep observations and sophisticated statistical models. It's a painstaking process of elimination, a cosmic trial where the defendant is utterly invisible. The other major challenge is that the most likely place to find these dark halos is not in isolation, but within the complex environments of massive galaxy clusters. In these dense regions, the gravitational lensing signal is a tangled web contributed by the cluster's main halo, its visible galaxies, and any potential dark subhalos. Disentangling the subtle lensing effect of a single, pure dark subhalo from this chaotic background is like trying to hear a single, quiet whisper in a roaring stadium. Should their existence be confirmed, pure dark halos would have profound implications. They would provide the cleanest possible laboratory for studying dark matter. Without the complicating effects of stars and gas and the violent feedback they produce, scientists could study the intrinsic properties of a dark matter halo in its most pristine state. Its shape and density profile would reflect only the fundamental nature of dark matter and the pure workings of gravity, unaltered by billions of years of astrophysical turbulence. This could finally help us resolve puzzles like the cusp core problem, telling us if the smooth centers of halos are an inherent feature or a later alteration. Furthermore, the mere existence of a population of dark halos would tell us something crucial about the galaxy formation process. It would imply that there is a critical mass threshold below which the universe simply cannot make a galaxy. Halos below this mass might form too late, after the available gas has been heated by the background radiation of the early universe, or their gravitational grip might be too weak to hold onto gas against internal pressures like supernova winds. Discovering these dark halos would be like finding the missing link in the hierarchy of cosmic structure, revealing the point at which the visible universe emerges from the dark. Now, as we grapple with the mysteries hidden within individual galaxies and their invisible halos, we must expand our view to the grandest scale of all, the universe in its entirety. This brings us to a crisis that strikes at the very heart of modern cosmology, a discrepancy so significant it has been dubbed the Hubble tension. At its core, this is a debate about a single, crucial number: how fast is the universe expanding right now? This rate, known as the Hubble constant, is the master key to understanding the cosmos's age, its size, and its ultimate fate. For years, we believed we were homing in on a precise value, but we now have two powerful, independent, and seemingly impeccable methods of measurement that are giving us two different, stubbornly incompatible answers. It's as if you used two different, perfectly calibrated rulers to measure the same table and got two different lengths that cannot be reconciled. This isn't a small margin of error. It's a fundamental disagreement that suggests we might be missing a crucial piece of physics. And many cosmologists are now asking a profound question. Could the answer lie in the intricate and perhaps imperfectly understood history of how dark matter halos grew? To understand the tension, we need to look at the two main ways we measure the Hubble constant. The first method looks into the deep past using the afterglow of the Big Bang itself, the cosmic microwave background. This faint radiation is a snapshot of the infant universe, and by meticulously analyzing its subtle patterns with satellites like Planck, we can extrapolate the universe's expansion history forward in time to predict what the Hubble constant should be today. This is a pristine, fundamental measurement based on the universe's initial conditions. The second method works in the local, present-day universe. It uses what are known as standard candle celestial objects like certain types of supernova and pulsating stars called cepheids, whose intrinsic brightness we believe we understand. By measuring how bright these objects appear from Earth and knowing how bright they truly are, we can calculate their distance. Combining this with measurements of how fast they are moving away from us gives us a direct local value for the expansion rate. The problem is stark. The local measurements consistently give a faster, more rapid expansion rate than the prediction from the early universe. The two methods disagree by a small but statistically significant amount. It's a discrepancy that has withstood over a decade of increasingly precise observations, growing from a faint worry into a full-blown crisis. This is where the growth of dark matter halos enters the picture. The prediction from the cosmic microwave background relies on a specific model of how structures, galaxies, and their halos formed over billions of years. This model, lambda-cold dark matter, makes certain assumptions. It assumes that dark matter is cold and collisionless, and that it clumps together in a predictable, hierarchical way, with small halos merging to form larger ones. But what if this assembly history is more complex than we've accounted for? The formation of halos is not a gentle process. It is a violent, chaotic saga of collisions and mergers. This activity doesn't just build structure, it also injects energy into the cosmic system. One compelling hypothesis suggests that if this process were more efficient or energetic than our models assume, it could have subtly warmed the cosmic environment, affecting how light and matter travel through the universe. This could potentially alter the apparent distances we measure to standard candles, creating a systematic shift in our local measurement of the Hubble constant. In this view, the tension isn't an error, but a clue that our simulation of cosmic structure formation is missing a key dynamic. Another fascinating angle considers the very nature of the dark components themselves. The lambda-CDM model is built on two pillars: dark matter to provide the gravitational scaffolding for structure, and dark energy to drive the accelerated expansion of the universe. The Hubble tension might be pointing to a flaw in our simple description of dark energy. What if dark energy is not a constant force, as represented by Einstein's cosmological constant lambda, but a dynamic field that has evolved over time? A dark energy that was stronger in the past could have influenced the rate at which dark matter halos assembled, changing the timeline of cosmic structure formation. This altered growth history would then leave an imprint on both the early universe snapshot and the local expansion rate, potentially bridging the gap between the two measurements. Alternatively, the problem could lie with dark matter. If dark matter has even small interactions with itself or with other particles, it could have altered the growth of the largest cosmic structures, the vast superclusters of galaxies. Any change in the timing or efficiency of this large-scale structure growth would inevitably affect the expansion history of the universe, creating a ripple effect that manifests as the Hubble tension we observe today. Resolving this crisis is one of the most urgent goals in cosmology. It forces us to question not just a single number, but the entire standard model of our universe. The Hubble tension is a powerful reminder that cosmology is a historical science. We are trying to reconstruct a 14 billion-year story from a series of scattered clues. The growth of dark matter halos is a central chapter in that story, and if we have misread it, the entire narrative may need revision. Whether the solution involves a new understanding of dark matter's properties, a dynamic form of dark energy, or a more complex picture of cosmic structure formation, the outcome will undoubtedly reshape our understanding of reality. The invisible architecture of the cosmos and the pace of its expansion are inextricably linked, and untangling this knot may require us to rewrite the rules of the universe itself. This leads us to another profound assumption we've been making, one that is so foundational it often goes unstated. What if dark matter halos aren't the simple, spherical structures we often picture them to be? This is our 11th mystery, the true shape of these invisible giants. In our minds, we might imagine a dark matter halo as a perfectly round, glowing sphere surrounding a galaxy, a cosmic soap bubble. This spherical assumption is mathematically convenient, and it works well enough for many basic calculations. But when we run our most sophisticated supercomputer simulations of cosmic evolution, which model the gravitational dance of billions of dark matter particles, a very different picture emerges. The halos that form are not serene spheres. They are chaotic, lumpy, and distinctly triaxial. Imagine a potato or perhaps a stretched-out football. They have three different axes, a long one, a medium one, and a short one, making them ellipsoids. Their shapes are not static either. They constantly shift and wobble as they interact with other halos and as new matter falls into them. This predicted triaxiality isn't just a minor detail, it's a fundamental prediction of the cold dark matter model. It arises naturally from the way structure forms in the universe. The initial seeds of density from the Big Bang were not perfectly symmetrical. As gravity amplified these tiny imperfections over billions of years, it pulled matter together along specific filaments of the cosmic web. A dark matter halo forms at the intersection of these filaments, and it grows by drawing material along these preferred directions. The result is a structure that reflects its violent, anisotropic birth. The exact shape of a halo can even tell us about its history. A halo that has recently undergone a major merger with another large halo might be more distorted and elongated. A quieter, more isolated halo might have had time to relax into a more rounded, but still not perfectly spherical, shape. But confirming this prediction observationally is one of the most difficult challenges in all of astronomy. How do you measure the shape of something you cannot see? The primary tool for this task is once again the subtle art of gravitational lensing. Specifically, we rely on a technique called weak gravitational lensing. While strong lensing creates dramatic arcs and rings around massive galaxy clusters, weak lensing produces an effect that is far more subtle. It doesn't create multiple images. It instead induces a tiny, coherent distortion in the shapes of thousands of background galaxies. The gravity of the foreground dark matter halo very slightly stretches these distant galaxies, making them appear ever so slightly aligned, like iron filings around a magnet. By meticulously measuring the patterns of these tiny stretches across a huge area of the sky, astronomers can statistically map the two-dimensional projection of the gravitational field, and from that infer the three-dimensional shape of the invisible mass causing it. The process is incredibly demanding. The lensing distortions are minuscule, often smaller than the intrinsic irregularities of the background galaxies themselves. It's like trying to measure the shape of a glass lens by looking through it at a field of pebbles, each of which is already a slightly odd shape. You need to observe thousands, even millions, of background galaxies to average out their random orientations and detect the coherent signal imposed by the dark matter halo. Furthermore, what we measure is only a two-dimensional projection of a three-dimensional shape. A triaxial halo can look very different depending on the angle from which we view it. A football-shaped halo pointed directly at us would appear round, while one seen from the side would look elongated. Disentangling this projection effect to determine the true, intrinsic three-dimensional shape requires combining lensing data with other clues, such as the motions of stars within the galaxy the halo hosts, adding another layer of complexity to the puzzle. The initial results from these ambitious observational campaigns have been both intriguing and somewhat contradictory. Some studies of massive galaxy clusters do suggest that their dark matter halos are indeed flattened and elongated, broadly consistent with the triaxial predictions from simulations. However, when astronomers look at the halos of individual, smaller galaxies, the picture becomes murkier. Some data seems to suggest that these halos might be more spherical than the simulations predict, or perhaps they are aligned in unexpected ways with the visible disk of the galaxy. This potential misalignment between the dark matter halo and the stellar disk is another fascinating puzzle. It challenges the idea that the visible galaxy simply forms at the center of a symmetrical gravitational well. Instead, it suggests that the process of galaxy formation, with its gas flows, mergers, and internal dynamics, can torque and twist the dark matter halo into a new orientation over time. The quest to measure the true shapes of dark matter halos is more than a technical exercise in mapping. It is a direct test of our understanding of how gravity assembled the universe. Every subtle distortion in the light of a distant galaxy is a clue to the form of the invisible hand that guides it. While our focus has been on the inner workings of dark matter halos, there is a critical frontier at their very edges, a boundary that defines the ultimate extent of a galaxy's gravitational domain. This brings us to our 12th mystery, the splashback radius. To understand this concept, we need to shift our perspective from the halo as a static object to a dynamic, living entity that is still growing. A massive dark matter halo, like the one surrounding a galaxy cluster, is not an isolated island. It sits at the heart of a vast cosmic watershed, where rivers of dark matter and gas flow along the filaments of the cosmic web, feeding its growth. Imagine a massive planet like Jupiter, with countless comets and asteroids falling towards it from the outer solar system. The splashback radius is the galactic equivalent of the point where an object falling into Jupiter's gravity well swings around the planet at its closest approach before, in theory, flying back out again. In the context of a dark matter halo, this point is known as the apocenter. In falling matter, whether dark matter particles or clumps of gas doesn't fall straight in. It has some angular momentum, so it swings around the halo in a wide orbit. The splashback radius is the spherical shell that marks the average apocenter of these recently infalling orbits. It's the boundary between matter that is still falling in for the first time and matter that has already completed its first pass and is now part of the halo's more relaxed inner population. Think of it as the outer edge of a whirlpool. Outside this edge, water is streaming inward. Inside, the water is chaotically swirling, having been incorporated into the vortex. For a galaxy cluster, the splashback radius is a fundamental feature. It marks its true physical boundary, the point where the density of matter drops off precipitously. It's the halo's actual edge, far sharper and more well-defined than the arbitrary boundaries astronomers often use for measurement. The mystery arises when we compare this theoretical prediction to real-world observations. Our most advanced cosmological simulations do predict the existence of a splashback radius, but when astronomers use clever techniques to measure it in actual galaxy clusters, for instance, by mapping the distribution of galaxies around them to trace the density drop, they often find something surprising. The observed splashback boundary appears to be even sharper and more pronounced than what the simulations show. It's as if the simulations predict a gradual transition from the rushing rivers of infall to the settled lake of the halo, but our telescopes reveal what looks more like a cliff face, a dramatic, sharp edge. This discrepancy suggests that our models of how matter accretes onto these colossal structures might be missing a key ingredient. The pure gravitational physics of collisionless dark matter may not be the whole story. One compelling explanation points back to the influence of ordinary matter, specifically the incredibly hot plasma that permeates galaxy clusters. As gas falls into a cluster, it doesn't just sail through unimpeded. It slams into the gas that's already there, creating immense shock waves, cosmic sonic booms that heat the gas to temperatures of tens of millions of degrees. This process, known as shock heating, is incredibly energetic. The idea is that this violent collision doesn't just affect the gas, it can also impact the dynamics of the infalling dark matter. The gravitational interaction between the dark matter and this suddenly heated, pressurized gas could act as a brake, causing the dark matter to lose energy and splash back more abruptly and coherently than it would in a model where only gravity is at play. In this scenario, the sharp edge we see is a signature of the complex interplay between dark and normal matter, a hydrodynamic effect that our simplified simulations of pure dark matter fail to capture. Another fascinating possibility is that this sharp boundary is telling us something new about dark matter itself. The standard model assumes dark matter is perfectly collisionless. Particles pass right through each other without interaction. But what if dark matter has even a tiny ability to interact with itself? This self-interaction would introduce a form of friction. As particles stream in and out of the halo at the splashback radius, this friction could cause them to exchange energy and slow down, piling up at the boundary and creating a steeper density drop. It would be akin to traffic slowing down and congesting at a merge point on a highway. Alternatively, if dark matter is not a simple, single type of particle but a more complex sector with multiple components, the interactions between these components at the halo's edge could also lead to a sharper transition. The splashback radius, therefore, is more than just a boundary. It is a sensitive probe of the physics governing both the visible and invisible components of the universe. Its unexpected sharpness is a clue that the final moments of a galaxy's growth are a more complex and violent process than we ever imagined. Pushing our investigation to the very dawn of time, we arrive at a mystery that the James Webb Space Telescope has hurled into the spotlight with stunning clarity. We are traveling back to the universe's infancy, to an era known as the Cosmic Dawn, to explore the formation of the very first dark matter halos. Our standard cosmological model, lambda cold dark matter, provides a detailed timeline for this process. After the Big Bang, the universe was a hot, dense, nearly smooth soup of particles. As it expanded and cooled, dark matter, being immune to the intense radiation pressure that kept normal matter scattered, began to clump together first. Tiny quantum fluctuations from the birth of the cosmos were amplified by gravity, serving as seeds. Over millions of years, these seeds grew into the first miniature dark matter halos, which then acted as gravitational traps, gathering the hydrogen and helium gas that would eventually collapse to form the very first stars and galaxies. This model predicts that this was a gradual process, with the first galaxies being small, faint, and taking their time to assemble. The James Webb Space Telescope, however, is showing us a very different picture of the universe's childhood. Instead of a cosmos populated by only small, infant galaxies, Webb's incredibly deep infrared gaze has revealed a surprising number of galaxies that are shockingly massive, brilliantly luminous, and already mature, existing at a time when the universe was only a few 100 million years old, a mere blink of an eye in cosmic terms. It's like opening a photo album of a child's first years and finding pictures of them as a fully grown adult. These galaxies are far too big, too bright, and too well structured to have formed according to our gradual timeline. Their existence poses a direct and profound challenge. How did the dark matter halos necessary to hold these colossal galaxies together assemble so incredibly fast? This discovery creates a serious tension with our models. For a galaxy to be that massive that early, an enormous dark matter halo must have already been in place to provide the gravitational foundation. But the cold dark matter paradigm has a specific prediction for how quickly these halos can grow. The growth is hierarchical. Small halos merge to form larger ones. This takes time. The existence of these behemoths so early in the universe suggests that the process was not just faster than we thought, but perhaps radically more efficient. It's as if the cosmic construction crew had access to technology we never anticipated, allowing them to erect skyscrapers in weeks instead of decades. This forces cosmologists to reconsider the very mechanics of halo assembly in the primordial universe. One possibility is that the initial conditions were more fertile than we realized. The seeds for structure, the primordial density fluctuations, might have been significantly larger on small scales than our measurements from the cosmic microwave background suggest. Those measurements are excellent for seeing the large-scale fluctuations, but they might be missing an enhancement of power on the smaller scales relevant for the first halos. If there were more pronounced lumps in the dark matter soup right after the Big Bang, gravity would have had a head start, causing halos to collapse and merge with breathtaking speed. Another, more exotic idea involves the nature of dark matter itself. Perhaps it wasn't perfectly cold. If dark matter was instead warm, with particles moving at a significant fraction of the speed of light, it would generally suppress the formation of the very smallest structures. However, under certain specific models, warm dark matter can actually accelerate the growth of the first medium-sized halos by streaming out of the tiniest clumps and speeding up the merger process for the next tier up. It's a counterintuitive effect, but it could provide a mechanism for faster early growth. A third, fascinating line of inquiry looks at the complex interplay between the dark matter and the first bursts of light. The formation of the first stars was a transformative event. These stars were likely monstrous behemoths, hundreds of times more massive than our Sun, and they lived short, violent lives, ending in spectacular supernovae. The intense ultraviolet radiation they emitted could have had a paradoxical effect. While this radiation heated the surrounding gas and generally made it harder for new stars to form elsewhere, a phenomenon known as the Lyman-Werner background, it might have also fundamentally altered the behavior of the normal matter in a way that accelerated galaxy growth. By destroying simple hydrogen molecules, the primary cooling agent for early gas, this radiation could have prevented gas from collapsing into countless small halos. Instead, the gas might have been forced to wait until it could fall into much larger, rarer halos that were massive enough to cool their gas through more complex atomic processes. This would funnel a vast amount of material into a few privileged locations, creating the massive galaxies we see with Webb in a surprisingly short time. The early universe, it seems, was not a gentle nursery but a chaotic and explosive environment where the rules of structure formation were written in fire and light. The James Webb Space Telescope, by revealing these galactic giants in the cosmic cradle, has not simply given us answers. It has handed us a deeper, more urgent question about how the invisible architecture of our universe was first assembled. But if the dark matter halo is a dynamic entity, constantly accreting new material, then we must also consider its destructive side. Within the vast gravitational dominion of a massive host halo, like the one surrounding our Milky Way, smaller subhalos are not merely passive satellites, they are engaged in a constant, losing battle for survival. This leads us to our 14th mystery, the ultimate fate of these dark matter subhalos as they are shredded by immense tidal forces. The process is a cosmic demolition project on an epic scale. As a small subhalo orbits through the dense inner regions of its massive host, it experiences a gravitational gradient. The pull on the side closest to the host center is significantly stronger than the pull on the far side. This difference in force stretches the subhalo, pulling it apart in a process known as tidal stripping. It's akin to the way the Moon's gravity stretches Earth's oceans to create tides, but on a vastly more violent and destructive level. The debris left behind from this demolition tells a fascinating story. As a subhalo is torn asunder, its dark matter particles don't just vanish. Instead, they are stripped away and deposited along the subhalo's orbital path, forming vast, ribbon-like structures known as tidal streams. Imagine a comet disintegrating as it swings close to the Sun, leaving a trail of dust and ice along its orbit. A dark matter tidal stream is the invisible gravitational equivalent, a river of pure dark matter flowing through the host halo. These streams can persist for billions of years, slowly phase, mixing and spreading out, but they remain as fossilized records of the accretion history of the host galaxy. The Milky Way's halo should be crisscrossed with thousands of such streams, a tangled web of cosmic archaeology revealing every significant merger and ingestion event over its entire lifetime. Detecting these pure dark matter streams, however, is one of the most formidable challenges in astronomy. Since they emit no light, we must rely on their gravitational influence. One promising method involves looking for subtle perturbations in the delicate stellar streams that we can see. When a small galaxy or star cluster is tidally stripped, it leaves behind a stream of stars. The gravity of a passing dark matter subhalo, or the broader influence of a dark matter stream itself, would gravitationally kick the stars in these visible streams, creating observable gaps, wiggles, or changes in their density. It's like deducing the presence of an invisible ship by watching the ripples it creates as it passes through a trail of floating leaves. Astronomers are actively searching for these anomalies in stellar streams around the Milky Way, and any confirmed detection would be a monumental step forward, providing a direct map of the invisible substructure within our own galactic backyard. The resilience of these subhalos and their streams also serves as a critical test for the nature of dark matter. The standard cold dark matter model predicts that subhalos should be incredibly resilient to tidal disruption. Because dark matter particles are thought to be collisionless, they can pass right through each other. This means a subhalo can lose its outer layers to tides, but its dense central core should survive for a very long time, orbiting as a distinct, self-bound entity even after most of its mass has been stripped away. Our simulations show this process clearly, populating large halos with countless such ghost subhalos that have been reduced to their dense centers. If, however, dark matter has any significant self-interaction, if the particles can collide and scatter, the story changes dramatically. Self-interactions would transfer energy within the subhalo, making it more malleable and puffy. A self-interacting dark matter subhalo would be far more vulnerable to tidal forces, dissolving completely much faster and potentially leaving behind smoother, more diffuse streams. Therefore, the population of surviving subhalos and the sharpness of the tidal streams we infer act as a natural laboratory. A halo teeming with ancient, stripped-down cores points to collisionless dark matter, while a relative absence of such structures might be the signature we need to confirm a more complex, interactive dark sector. The silent, slow-motion destruction of these invisible islands holds the key to understanding the fundamental physics of the universe's most elusive component. This intricate dance between the visible and invisible components of a galaxy finds its most extreme expression at the very center, where a gravitational monster often resides. This brings us to a truly baffling correlation that hints at a deep, underlying connection between the largest and smallest scales, the mysterious link between supermassive black holes and their dark matter halos. At the heart of most large galaxies, including our own Milky Way, lies a supermassive black hole, an object so dense that its gravity prevents even light from escaping. For decades, astronomers have noted a surprising and seemingly improbable relationship. The mass of a galaxy's central black hole is closely correlated with the properties of the galaxy's bulge, the central swarm of stars. But more recently, an even more profound connection has emerged. The mass of the central black hole also appears to be correlated with the total mass of the entire dark matter halo that envelops the galaxy. This is staggering. Imagine finding a rule that linked the size of a single cherry pit to the total mass of the entire tree, including its invisible root system spreading deep underground. How could an object that is 1 billion times smaller than the galaxy it lives in possibly know about the immense invisible structure that surrounds it? This correlation is deeply puzzling because the scales involved are so vastly different. The event horizon of a supermassive black hole might span a distance smaller than our solar system, while its dark matter halo extends for hundreds of thousands of light years. The black hole's gravitational influence is utterly dominant in its immediate vicinity, but it is negligible on the scale of the entire halo, so the link cannot be a simple, direct gravitational conversation. Instead, it points to a shared history, a common set of physical processes that govern the growth of both the visible galaxy and its dark foundation from the very beginning. One compelling line of thought suggests that dark matter itself may have played a crucial role in seeding these cosmic behemoths. In the very early universe, before the first stars ignited, the first structures to collapse under gravity were the small, pristine halos of dark matter. Within these halos could direct collapse have occurred. Perhaps under certain rare conditions, vast clouds of pure hydrogen gas, funneled by the dark matter's gravity, collapsed directly into a massive black hole seed, bypassing the stage of star formation entirely. These initial seeds, weighing perhaps thousands of solar masses, would then have a tremendous head start, growing over billions of years into the supermassive black holes we see today. In this scenario, the dark matter halo acts as the initial catalyst, its gravitational potential well determining the maximum amount of gas that can be gathered, and thus setting the stage for the black hole's birth mass. Another perspective focuses on the dark matter halo not as a midwife but as a regulator. The growth of a supermassive black hole is not a gentle process. It is an active, violent phase of accretion that releases unimaginable amounts of energy. As we discussed with baryonic feedback, this energy floods out into the galaxy, heating gas and potentially shutting down star formation. This creates a powerful feedback loop. The black hole feeds and grows, but in doing so, it unleashes energy that pushes away the very gas it needs to consume, ultimately limiting its own growth. The properties of the dark matter halo, its total mass and its gravitational pull, may set the ultimate ceiling for this process. A more massive halo can hold onto a larger reservoir of gas, allowing for a longer and more substantial period of black hole growth before feedback halts it. Conversely, a smaller halo might have its gas supply more easily disrupted, leading to a proportionally smaller black hole. The correlation, then, is not a direct link but an emergent property of a self-regulating system, where the dark matter halo defines the size of the playing field, and the complex physics of black hole feedback determines the final score. Yet the possibility remains that this mysterious connection points to something even more fundamental, a third, unknown factor that governs the growth of both structures simultaneously. The initial conditions of the universe, the spectrum of primordial density fluctuations imprinted by the Big Bang, could have set the rhythm for all subsequent structure formation. A region of space that was destined to collapse into a particularly massive dark matter halo might have also been endowed with a denser peak of normal matter at its very center, predisposing it to form a more massive black hole seed from the outset. The dark matter halo and the black hole would then be siblings born from the same cosmic blueprint, their fates intertwined from the moment of creation. This idea pushes the limits of our understanding, suggesting that the largest structures in the universe and the most extreme objects within them are different manifestations of the same underlying physics, a hidden harmony in the laws of nature that we are only just beginning to perceive. Unraveling this connection is more than an academic exercise. It is a quest to understand how the universe choreographs its growth, linking the infinitesimal to the infinite through forces we have yet to fully comprehend. Yet another layer of complexity in the dark matter saga reveals itself not in the silent distribution of mass, but in the frantic motions of the objects trapped within the halo's gravitational grip. If a dark matter halo were a perfectly calm and serene sphere that had assembled gently, you would expect the orbits of the stars and satellite galaxies within it to be equally serene and random. Their velocities would be the same in every direction, a state physicists call isotropic. It would be like a swarm of gnats buzzing in a perfectly spherical cloud. No matter which way you look, the motion appears the same. This simple, isotropic assumption has been a cornerstone of many models used to weigh galaxies and map their dark matter content. But the universe, it seems, has little patience for such simplicity. When astronomers measure the velocities of stars in the outer reaches of our Milky Way, or trace the paths of satellite dwarf galaxies, they find something much more chaotic. The speeds are not the same in all directions. Instead, the motions are anisotropic, meaning there is a preferred direction, a cosmic current flowing through the invisible sea of dark matter. This discovery is like realizing that the gnats aren't buzzing randomly at all, but are instead all streaming along an invisible wind, a clue that the placid sphere we imagined is actually a dynamic system with a violent and directional history. This anisotropy is a direct fingerprint of how the halo was built. A galaxy's dark matter halo is not born in isolation. It is the product of a dramatic and messy construction process that continues to this day. The primary source of this directional motion is the cosmic web itself. Dark matter and gas flow into the growing halo along specific, narrow filaments like rivers feeding a lake. When a smaller galaxy or a clump of dark matter falls in along one of these filaments, it doesn't immediately forget its original trajectory. It carries that directional momentum with it, contributing to a larger scale flow within the halo. Over time, as multiple streams of material fall in from different directions, their combined motions can create a complex and anisotropic velocity field. It's the gravitational equivalent of pouring water into a bowl from several different angles. The water will slosh and swirl with a distinct pattern, rather than settling into a perfectly featureless pool. The anisotropic velocities we measure today are the lingering echo of these ancient accretion events, a fossil record of the paths our galaxy took to gather its mass. The most striking evidence for this comes from our own cosmic backyard. Detailed surveys of stars in the Milky Way's halo have revealed vast groups of stars moving in coherent streams, all sharing similar velocities and directions. These are the shredded remains of small galaxies that our Milky Way has cannibalized over billions of years. But beyond these obvious streams, there is a broader, more subtle pattern. Studies suggest that the motions of stars and satellite galaxies in the outer halo are not random. They appear to be aligned, perhaps even rotating, much like the planes of satellites we discussed earlier. This coherent motion is incredibly difficult to explain if the halo assembled from a smooth, spherical collapse. Instead, it points to a few major accretion events that delivered a huge amount of mass and a specific directional momentum in a relatively short period of time. Our galaxy's halo, therefore, might not be a well-mixed cocktail, but a layered drink where you can still taste the distinct ingredients that are poured in. This realization has profound implications for how we measure the properties of dark matter halos, particularly their mass. For decades, a standard technique for weighing a galaxy has been to use the motions of its stars as a gravitational thermometer. The basic idea is that the faster the stars are moving, on average, the more mass must be present to hold them in orbit. This method, however, often relies on the assumption that the velocities are isotropic. If the motions are actually anisotropic, if the stars are preferentially streaming in one direction, then a simple measurement of their speed can lead to a significant miscalculation of the halo's total mass. Imagine trying to measure the energy of a crowd by only listening to the noise. If everyone is milling about randomly, the noise gives you a good estimate. But if the entire crowd is marching in a parade, the noise level might be the same, but the nature of the motion is entirely different, and you would be wrong to assume it represents chaotic energy. Similarly, anisotropic flows can mimic the overall velocity dispersion of an isotropic system, but they imply a very different gravitational history and can bias our estimates of the halo's weight, potentially leading us to overestimate or underestimate the amount of dark matter present. The presence of strong anisotropy is more than just a complication for astronomers. It is a powerful diagnostic tool. The specific pattern of the velocities can tell us about the number and nature of the major merger events that built the halo. A halo that shows a high degree of anisotropy likely had a more chaotic and violent assembly history, dominated by a few large mergers from specific directions. A halo with more isotropic velocities might have had a quieter life, growing through a steady trickle of smaller accretions from all directions. By carefully mapping the velocity fields of galaxies, we are essentially reading their autobiographies written in the language of motion. This challenges the old picture of a galaxy as a stately, isolated island universe and replaces it with a dynamic portrait of a constantly evolving structure whose present-day state is a palimpsest of its violent past. The anisotropic dances of stars and satellites are a direct window into the epic construction project that built the cosmic structures we see today, a project directed by the unseen hand of dark matter. But this grand cosmic dance of accretion and disruption ultimately leaves its mark on a specific, measurable property of the halo, its density from the core to the outer edge. This brings us to a formula that has achieved near-mythic status in cosmology, a mathematical key that was supposed to unlock the secrets of all dark matter halos. We now arrive at our 17th mystery, the challenge to the universal density profile. For decades, our understanding of halo structure has been dominated by a single, elegant equation known as the Navarro-Frenk-White profile, or the NFW profile for short. Developed in the 1990s from groundbreaking supercomputer simulations, this formula describes how the density of dark matter changes as you move from the halo's outer reaches toward its very center. It predicts a specific characteristic shape. The density rises steadily as you move inward, following a smooth, continuous curve that becomes increasingly steep near the very center, forming that characteristic cusp we discussed earlier. The true power of the NFW profile was its claimed universality. The simulations suggested that every dark matter halo, from the smallest dwarf galaxy to the largest galaxy cluster, regardless of its mass or violent history, would have a density distribution that could be described by this one mathematical form. It was a revelation, a unifying principle that promised to simplify the complex cosmos into a single, elegant rule. However, the real universe, with its endless capacity for surprise, has begun to chafe against this mathematical straitjacket. The most significant challenges come from the extremes of the size spectrum, the smallest dwarf galaxies and the most massive galaxy clusters. Let's start with the dwarfs. These faint, diffuse galaxies are ideal laboratories because they are thought to be overwhelmingly dominated by dark matter, with very little of the messy astrophysics from stars and gas to complicate the picture. If the NFW profile is truly universal, these galaxies should show a clear, steeply rising density cusp in their centers. Yet, as we've touched on, observations repeatedly suggest the opposite. The inner regions of many dwarf galaxies appear to have a much flatter, constant density core. It's as if the predicted mountain peak has been planed off into a plateau. This core-cusp problem is a direct assault on the universality of the NFW profile. If the formula fails for the very objects that should be its purest examples, then its claim to universality is severely weakened. The plot thickens when we look at the other end of the scale, immense galaxy clusters. These are the largest gravitationally bound structures in the universe, containing the mass of 1,000 galaxies or more. Here, the challenge to the NFW profile is more subtle but equally profound. While the overall shape might seem to fit, detailed observations, particularly from gravitational lensing and the motions of stars within the cluster's central galaxy, often suggest that the inner densities are too high compared to the NFW prediction. The halo seems to be even more concentrated, more densely packed at its heart than the universal formula allows. This is the inverse of the dwarf galaxy problem. Instead of a profile that is too flat, we see one that is too steep. This discrepancy hints that the formation history of these colossal structures might involve physics that the simple NFW simulations did not capture, such as the relentless influx of gas and smaller halos that can drag dark matter inward, increasing the central concentration over time. So, what could be causing this breakdown of universality? The answer likely lies in the fact that the real universe is far more complex than the pristine simulations that birthed the NFW profile. Those pioneering simulations modeled a universe containing only dark matter governed solely by gravity. they were a beautiful, simplified experiment. But our actual cosmos is filled with normal matter baryons, and baryons are anything but simple. As we've explored, the process of galaxy formation is a violent affair. The explosive deaths of stars in supernova and the ferocious energy output from supermassive black holes can inject tremendous energy into the galactic center. This baryonic feedback doesn't just affect the gas, it gravitationally interacts with the dark matter, potentially transferring energy and pushing it outward, thereby flattening the central cusp into a core. This effect would be most pronounced in smaller galaxies with shallow gravitational wells, perfectly explaining the observations in dwarf galaxies. Conversely, in the massive, deep potential wells of galaxy clusters, the opposite can occur. During the cluster's assembly, the infall of enormous amounts of gas can adiabatically drag dark matter along with it, pulling it deeper into the center and creating an over-concentrated profile that exceeds the NFW prediction. The other compelling possibility is that the NFW profile's failure is a direct clue to the intrinsic nature of dark matter. The profile is a specific prediction of the standard cold dark matter model. If dark matter has different properties, if it is warm, for instance, with particles moving fast enough to resist clumping on the smallest scales, then the inner density profiles of halos would naturally be shallower from the outset. Alternatively, if dark matter particles can interact with each other, these self-interactions would act as a form of pressure, smoothing out the dense central cusps and creating the flat cores we observe. The mounting evidence against a perfectly universal density profile is therefore not a crisis but an opportunity. It is forcing us to move beyond a simplistic one-size-fits-all model and develop a more nuanced understanding of halo structure, one that incorporates the dynamic history of baryonic feedback and remains open to the possibility that dark matter itself is a more complex and interesting substance than we first imagined. The quest to map the true density of dark matter halos is far from over. It is evolving into a deeper inquiry into the fundamental physics that governs both the seen and the unseen universe. The ultimate test of dark matter's existence, and perhaps the most visually stunning piece of evidence we have, comes not from isolated galaxies but from the most violent events in the universe, the collisions of entire galaxy clusters. These are the cosmos's largest and most energetic smash-ups, and they provide a unique, natural laboratory where we can watch dark matter and normal matter behave in fundamentally different ways. The most famous and decisive example of this is a system known as the Bullet Cluster. This isn't a single galaxy, but two massive clusters that have recently plowed right through each other at unimaginable speeds. The collision released more energy in a few moments than 1 billion stars would over their entire lifetimes, and it is in the aftermath of this cosmic catastrophe that dark matter was caught, quite literally, separating itself from everything else. To understand what happened, we need to think about the different components that make up a galaxy cluster. First, there are the galaxies themselves, which are mostly empty space. Each galaxy contains billions of stars, but the distances between those stars are so vast that when two clusters collide, the galaxies themselves pass right through one another like two swarms of gnats, largely unaffected. The second component is the hot gas that fills the space between the galaxies. This isn't thin, wispy gas. It's a superheated plasma, often called the intracluster medium, that contains the majority of the cluster's normal matter. This gas is what creates the drama. When the clusters collide, this hot gas smashes together. The particles interact electromagnetically, creating immense friction and pressure, slowing the gas down dramatically. It's like two clouds of smoke colliding. They merge, get tangled, and slow to a halt right in the middle of the collision site. Now, where is the dark matter in all of this? We can't see it, but we can map its location with extreme precision using the phenomenon of gravitational lensing. By observing how the immense gravity of the cluster warps the light from galaxies far behind it, astronomers can create a detailed mass map showing where the bulk of the matter is concentrated. When scientists did this for the Bullet cluster, the result was breathtaking. The map revealed that the majority of the mass, the dark matter, was not in the center of the collision where the hot gas had piled up. Instead, the dark matter was located in two distinct clumps, each coinciding with the positions of the galaxies that had sailed almost unscathed through the collision. This means the dark matter, like the galaxies, felt so little interaction that it kept right on going, leaving the normal gas behind. This observation is a monumental confirmation of dark matter's existence. It powerfully rules out theories like modified Newtonian dynamics or MUND, which propose modifying gravity as an alternative to dark matter. If MUND were correct, the gravitational lensing signal would be strongest where the most mass is, and in a cluster collision, the most mass is in the form of the hot gas that is stuck in the middle. The fact that the gravity is strongest where the galaxies are, and not the gas, is a direct demonstration that the dominant source of gravity is something other than the visible matter. That something is dark matter, and the Bullet cluster shows it behaves exactly as a collisionless particle should. It feels gravity but nothing else. However, this incredible success story also raises new, more subtle questions. If dark matter is truly collisionless, how does it behave during these immensely violent events? The fact that the dark matter clumps remained coherent and didn't get significantly scrambled or heated up by the collision tells us that any self-interaction between dark matter particles must be incredibly weak. But is it completely zero? Studies of other colliding clusters have revealed some intriguing anomalies. In a system known as the Abell 520, while the collisions of galaxy clusters give us a powerful gravitational picture of dark matter, scientists have been hunting for a much more direct signal, a faint spark of light emitted by the particles themselves. This brings us to our 19th mystery, the perplexing silence in the search for dark matter annihilation. The concept is one of particle physics' most elegant ideas. If dark matter is indeed made of particles, and if those particles are their own antiparticles, then whenever two of them collide, they could annihilate each other in a flash of energy, converting their mass directly into secondary particles like gamma rays, the most energetic form of light. The most promising places to look for this feeble glow are the regions where dark matter is most densely packed, the very hearts of galaxies and their halos, where the concentration of particles should be highest, making collisions and annihilations more frequent. For over a decade, astronomers have trained our most sensitive gamma-ray telescopes, like the Fermi Gamma Ray Space Telescope, on the most likely targets. They have scanned the center of our own Milky Way, studied nearby dwarf galaxies that are rich in dark matter, and peered at massive galaxy clusters. The logic was impeccable. Point your detector where the dark matter is densest and wait for the telltale signature of annihilation to reveal itself. Yet, despite this extensive search, the result has been a profound and puzzling silence. We have not detected the unambiguous gamma-ray signal that would confirm dark matter's particle identity. It's as if we have a theory predicting a specific radio station should be broadcasting from a known location, but when we tune our most advanced receiver to that frequency, we hear only static. This non-detection is in itself a major clue, forcing a significant rethink of what dark matter might be. The most immediate implication of this silence is that dark matter particles must be even more elusive than we had hoped. For the annihilation process to work, the particles not only need to collide, but they also need to interact with a specific strength. The lack of a signal suggests that this interaction strength, what physicists call the annihilation cross-section, is much, much smaller than many popular models predicted. It means that dark matter particles, on the rare occasions they do bump into each other, are far less likely to annihilate. Alternatively, the particles might not be their own antiparticles at all, which would mean annihilation simply cannot occur. Or the mass of the dark matter particle could be different from what we've been searching for. If the particles are either very light or extremely heavy, the gamma rays they would produce could fall outside the energy range our current telescopes are designed to detect, making them invisible to our present technology. Another fascinating possibility involves the very distribution of dark matter within these dense regions. Our searchers rely on the assumption that dark matter forms a steep, dense cusp at the center of halos as predicted by the NFW profile. But what if the reality is different? If processes like baryonic feedback have, in fact, smoothed out the central cusp into a core, as observations of dwarf galaxies suggest, then the dark matter density in the very center might be significantly lower than we think. A lower density means far fewer particle collisions, dramatically reducing the expected annihilation signal. In this scenario, our telescopes aren't failing to see a bright signal. The signal itself is inherently fainter because the dark matter isn't packed as tightly as our models assumed. The search for annihilation is therefore intertwined with the cusp core problem, where solving one mystery might help explain the silence of the other. Beyond these adjustments to the standard theory, the absence of an annihilation signal has opened the door to more exotic candidates. The focus is shifting from the once favored WIMP to other hypothetical particles. Actions, for instance, are a prime example. These hypothetical particles are thought to be incredibly light, and they would not annihilate to produce gamma rays in the same way. Instead, actions could convert into photons in the presence of strong magnetic fields. This presents a completely different search strategy, looking for a faint radio signal rather than a gamma ray flash. The lack of a gamma ray signal doesn't rule out actions, it just means we need to use a different kind of net to catch them. Other theories propose that dark matter might be part of a complex, hidden sector with its own unique forces and particles. Annihilations in this scenario might produce exotic particles that then decay into standard particles in a way that doesn't yield a clear, concentrated gamma ray signature that our telescopes can easily pinpoint. The enduring mystery of dark matter annihilation is a classic example of how a null result in science can be just as provocative as a discovery. It has pushed physicists to refine their models, to consider a wider range of possibilities, and to design ever more clever and sensitive experiments. This search is far from over. New telescopes, both on the ground and in space, are being developed with enhanced capabilities to probe different energy ranges and fainter signals. The silence we hear today is not an endpoint. It is a powerful message telling us that the dark universe is even more subtle and strange than we imagined, and that the ultimate discovery will require us to listen more carefully and in new ways than ever before. Faced with these persistent small-scale puzzles, the missing satellites, the too-big-to-fail galaxies, and the unexpectedly smooth cores of dwarf galaxies, cosmologists have been forced to revisit a fundamental assumption: the very temperature of the dark matter particle itself. This brings us to a compelling alternative to the long-dominant paradigm, an idea known as warm dark matter. For decades, the leading candidate has been cold dark matter, which envisions particles that were moving sluggishly, almost imperceptibly, when the first structures began to form. This slowness allowed them to clump together effortlessly, from the largest galaxy clusters down to the tiniest planet-sized halos. But what if that assumption is what's causing the mismatch? What if dark matter particles were born with a bit more zip, a bit more thermal energy in the early universe? The concept of warm dark matter offers an elegant solution to several of our most stubborn mysteries. If dark matter particles are lighter and faster moving, they would have behaved differently in the primordial cosmos. This extra motion, this inherent warmth, would have a smoothing effect. Think of it like trying to build a sandcastle with dry, fine sand versus wet, heavy sand. The cold dark matter is like the wet sand. It sticks together easily, forming clumps of all sizes, even very small, fragile ones. Warm dark matter, however, is like the dry, hot sand. The individual grains have more energy, making it difficult to form the smallest, most delicate structures. The smallest gravitational potential wells simply wouldn't be deep enough to hold onto these faster-moving particles. As a result, the formation of the very tiniest dark matter halos would be suppressed. This would naturally explain why we see far fewer small satellite galaxies around the Milky Way than the cold dark matter model predicts. The countless missing satellites weren't failed to form stars. Their dark matter foundations may never have fully coalesced in the first place. This smoothing effect would also extend to the internal structure of the halos that do manage to form. The frenetic motion of warm dark matter particles would prevent them from settling into an extremely dense, sharp cusp at the center of a halo. Instead, they would form a shallower, flatter core from the outset, neatly aligning with the observations of many dwarf galaxies and potentially resolving the cusp core problem without needing to invoke complex baryonic feedback. It's a beautifully simple fix. The properties of the particle itself could inherently produce the galactic structures we actually observe. However, like any good theory, warm dark matter must survive a series of rigorous observational tests, and here the plot thickens. The most powerful constraints come from the farthest reaches of the universe, from the intricate patterns of the cosmic microwave background and the distribution of distant, ancient gas clouds known as the Lyman Alpha Forest. These observations probe the universe when it was very young, and they are exquisitely sensitive to the amount of small-scale structure present at that time. If warm dark matter suppresses too much small-scale power, it would leave a clear imprint on these cosmic fossils, an imprint that so far has not been convincingly detected. The data strongly favors a model where there was a significant amount of small-scale clumpiness in the early universe, which aligns much better with the cold dark matter scenario. This creates a delicate balancing act for warm dark matter theorists. The particle must be warm enough to solve the small-scale problems we see in today's universe, but not so warm that it erases the small-scale structure that the early universe data demand. It's a cosmic tightrope walk. The current constraints suggest that if warm dark matter is real, the particle must be remarkably fine-tuned. Its mass would need to be in a specific range, heavy enough to not completely wipe out the small galaxies we know must have existed early on to light up the universe, but light enough to still suppress the formation of the multitudes of tiny, dark halos that plague the cold dark matter model. This narrow window of viability makes the warm dark matter hypothesis both tantalizing and fragile, a solution that could be overturned by the next, more precise measurement of the high redshift universe. The debate between cold and warm dark matter is far from settled, and it highlights a deeper philosophical shift in cosmology. We are moving from simply confirming the existence of dark matter to precisely characterizing its properties. The small-scale problems of galaxies are no longer seen as mere annoyances to be explained away by complex astrophysics. They are potential smoking guns, clues pointing toward the fundamental nature of the universe's dominant matter component. Whether the final answer lies with cold, warm, or perhaps an even more exotic variety of dark matter, this investigation is pushing our understanding of cosmic structure formation to its limits, forcing us to consider that the invisible skeleton of the cosmos may have a more dynamic and thermal history than we ever imagined. Now, as we strive to understand dark matter by studying individual halos and their peculiarities, we must also learn to count them. This brings us to a fundamental statistical tool in cosmology, a kind of cosmic census that reveals the demographics of the invisible universe, the halo mass function. In its simplest terms, the halo mass function is a prediction of how many dark matter halos of a given mass exist in a given volume of space. It tells us, for instance, whether the cosmos contains more galaxy-sized halos or cluster-sized halos, and exactly how many of each we should expect to find. This function isn't just a random guess, it is a direct mathematical consequence of the initial conditions of the Big Bang and our specific model of dark matter. According to the prevailing lambda-cold dark matter model, the universe should be teeming with an enormous number of very small, low-mass halos, with the number of halos steadily decreasing as we look toward higher and higher masses. The most massive halos, the great galaxy clusters, should be incredibly rare, the cosmic equivalents of Mount Everest. This predicted distribution is not just a theoretical curiosity. It is a powerful bridge that connects the invisible world of dark matter to the visible world of galaxies. Astronomers make a critical and perhaps overly simplistic assumption that every dark matter halo above a certain mass threshold will eventually host a galaxy. Therefore, by counting the number of galaxies of different brightnesses and sizes, we should be able to work backwards and infer the underlying halo mass function. We can also probe it more directly through the subtle warping of space-time via weak gravitational lensing surveys, which statistically weigh the halos along our line of sight, even if they are completely dark. For decades, this approach has been a cornerstone of modern cosmology, with observations broadly confirming the predicted shape of the mass function on the largest scales. The agreement was seen as a triumphant validation of our entire cosmological model. However, as our observational techniques have grown more precise, subtle but significant tensions have begun to emerge, particularly at the extremes of the mass spectrum. On the low mass end, the problem echoes the missing satellites dilemma. The predicted halo mass function suggests the universe should be absolutely filled with countless trillions of tiny, low-mass halos, some no heavier than a large asteroid. But when we look at the population of small, faint dwarf galaxies, their numbers fall far short of this prediction. This could be explained, as we've discussed, by the inefficiency of galaxy formation in these shallow gravitational wells. But it leaves open a haunting possibility. Does the discrepancy mean these tiny halos never formed at all, pointing toward a warmer type of dark matter, or are they out there in unimaginable numbers, forever dark and invisible to us? The halo mass function, in this regard, presents us with a profound uncertainty about the very smallest building blocks of cosmic structure. On the opposite end of the scale, with the most colossal halos hosting immense galaxy clusters, a different kind of tension is brewing. Some of the largest and most recent galaxy surveys, which map the positions of millions of galaxies, have hinted that the number of extremely massive clusters might be slightly higher than what the standard lambda-cold dark matter model predicts. Finding more of these cosmic giants than expected is like taking a census of a country and discovering several extra megacities that your demographic models said shouldn't exist. This could be a statistical fluke, but if it holds up, the implications are serious. The abundance of the most massive clusters is exquisitely sensitive to the exact values of key cosmological parameters, such as the overall density of matter in the universe and the amplitude of the initial primordial fluctuations. An overabundance of giants could mean that the universe is slightly more clumpy than we thought, or that the mysterious force of dark energy has a more complex history, influencing the growth of these structures in ways we haven't accounted for. These tensions force cosmologists to confront the messy reality of galaxy formation. The simple one-to-one mapping between a halo's mass and the galaxy it hosts is likely a gross oversimplification. The final properties of a galaxy, its brightness, its size, its star formation rate, are not determined by mass alone. They are sculpted by a galaxy's entire history, its merger history, the efficiency of star formation within it, and the transformative effects of baryonic feedback from supernova and supermassive black holes. A massive halo that experienced intense feedback might host a galaxy that looks deceptively faint for its weight, while a somewhat smaller halo that formed stars efficiently could appear brighter. This complex astrophysics introduces a scatter in the relationship. blurring the clean lines of the theoretical halo mass function and making direct comparisons with observations incredibly challenging. Disentangling this cosmic scatter from a genuine flaw in our fundamental cosmological model is one of the most active and difficult frontiers in astrophysics today. The halo mass function, therefore, is more than a simple curve on a graph. It is a critical stress test for our entire understanding of the universe, a test where even the smallest deviation could point toward a revolutionary new chapter in physics. While we have been surveying the grand cosmic landscape, some of the most revealing clues about dark matter are being uncovered right here in our own celestial backyard. As we turn our gaze inward to the Milky Way, we encounter a mystery written in the very motions of the stars around us, a ghostly signature of a catastrophic galactic collision that has profoundly shaped our home. This brings us to the fascinating story of the Gaia sausage, a discovery that has revolutionized our understanding of the Milky Way's dark matter halo and provided a stunningly precise window into its hidden structure. The hero of this story is the European Space Agency's Gaia mission, an ambitious project to create an unprecedented three-dimensional map of our galaxy. Gaia has meticulously charted the positions, distances, and, most importantly, the velocities of nearly 2 billion stars. By analyzing this colossal dataset, astronomers performed a kind of galactic archaeology, sifting through the stellar population to uncover its history. What they found was astonishing. Instead of a random mix of orbits, they identified a distinct, vast population of stars, all moving in highly eccentric radial orbits, plunging dramatically toward the galactic center and then swinging far out into the halo. When plotted in a graph of their orbital velocities, this group of stars formed a distinctive, elongated shape that reminded researchers of a sausage, giving the structure its memorable name. But this was no mere curiosity. It was the glittering debris of a dwarf galaxy that met its end billions of years ago. This discovery tells a dramatic tale of the Milky Way's violent youth. The Gaia sausage is the remnant of a significant galaxy, unofficially named Gaia Enceladus, that once orbited our own. This galaxy was not a small, insignificant speck. It was a substantial system, perhaps 1/4 the mass of the Milky Way's stellar disk at the time. Billions of years ago, this galaxy ventured too close to our growing Milky Way. The immense tidal forces of our galaxy's dark matter halo acted like a cosmic grinder, violently tearing the dwarf apart. Its stars were not assimilated gently. They were scattered into the chaotic, swirling orbits we see today, forming the inner foundation of our galaxy's stellar halo. This single, ancient merger is now understood to be one of the most defining events in the Milky Way's history, responsible for shaping a significant portion of the stars we see around us. The true power of this discovery, however, lies not just in the stars we can see, but in what they reveal about the invisible gravitational field that governs them. The specific radial orbits of the sausage stars are like a fleet of high-precision probes, meticulously mapping the shape of our dark matter halo. Stars on such stretched-out, plunging orbits spend most of their time moving slowly at the far reaches of their trajectory, where the galaxy's gravity is weakest. This makes their paths exquisitely sensitive to the exact distribution of mass in the halo. By tracing the orbits of these stellar fossils, astronomers can perform a detailed gravitational autopsy, reconstructing the three-dimensional shape and density of the dark matter cocoon in which we are embedded. What this stellar evidence suggests is that our halo is not a perfect sphere. The orbits of the sausage stars are consistent with a halo that is slightly flattened or squashed along its rotational axis, a shape known as an oblate spheroid. Think of it as a sphere that has been gently pressed down at the poles, much like the shape of the Earth itself. This flattening provides a critical clue about the Milky Way's formation. A spherical halo might suggest a quiet, isolated collapse, while a flattened one indicates a more dynamic history, likely influenced by the rotational momentum imparted by major accretion events, exactly like the Gaia-Enceladus merger. The persistence of these radial orbits over billions of years also tells us that the inner region of our dark matter halo is remarkably smooth. If it were filled with a large number of massive, lumpy dark matter subhalos, their gravitational kicks would have perturbed the sausage star's orbits, randomizing them over time. The fact that the radial structure remains so coherent suggests that the inner halo is a quieter gravitational environment than some simulations predicted, offering a new constraint for our models of dark matter substructure. The Gaia sausage has therefore transformed our perspective. It has turned the halo from a static, theoretical concept into a dynamic, measurable entity with a rich history. This single structure connects a dramatic event from the deep past to the present-day distribution of dark matter, providing a tangible link between the visible and invisible components of our galaxy. It demonstrates that the key to understanding the largest mysteries of the cosmos may not always lie in the most distant galaxies, but in the intricate dance of the stars right next door, each one a silent witness to the powerful, unseen forces that have sculpted our home in the universe. Shifting our perspective from the bustling metropolises of galaxy clusters and the intricate suburbs of our own Milky Way, we venture into the cosmic countryside, the vast, desolate regions known as cosmic voids. These are the universe's true empty quarters, unimaginably huge volumes of space that can span hundreds of millions of light years, containing almost nothing. If a galaxy cluster is a brilliant city and a spiral galaxy like our own is a thriving town, then a cosmic void is a continent-sized desert, so empty that a single, small galaxy within it would feel like a lone shack in an endless, featureless plain. It is within these profound emptinesses that we encounter a fascinating and counterintuitive mystery. Do dark matter halos even exist here? And if they do, are they fundamentally different from their cousins in the crowded cosmic cities? The answer pushes our understanding of structure formation to its absolute limits. The existence of halos in voids seems at first to defy the very process that builds the cosmos. Our standard model of cosmic evolution is driven by gravity's relentless pull, which amplifies tiny, dense regions into grand structures. Voids, by definition, are the underdense regions, the valleys in the cosmic web where the initial density fluctuations were negative. As the universe expanded, gravity acted in reverse here. Instead of pulling matter in, it allowed matter to flow out towards the denser filaments and nodes, leaving behind an ever emptier expanse. So, logically, one might expect voids to be completely devoid of dark matter halos, barren of any significant structure whatsoever. Yet, our most sophisticated simulations tell a more nuanced story. They predict that even in the deepest voids, a sparse population of dark matter halos does manage to form. These are the universe's true hermits, halos that condensed from the faintest of ripples in the primordial soup, isolated from the main action of cosmic construction. The properties of these void halos, however, are anything but normal. Because they formed in an environment starved of raw material, they are expected to be significantly less massive than halos of similar age in average regions of space. But the differences run much deeper than just mass. A halo's growth is not just about how much mass it accumulates, but also how it accumulates it. In a dense cluster environment, a halo grows rapidly through frequent, violent mergers with other halos, a chaotic process that constantly stirs and reshapes it. A void halo, in stark contrast, has a much quieter life. It experiences what cosmologists call slow, smooth accretion. It grows gradually, like a lonely snowball rolling across a flat plain, picking up a thin dusting of dark matter over billions of years without any major collisions. This peaceful existence has profound consequences for its internal structure and the galaxy it might host. This unique formation history makes void halos exceptional natural laboratories. They are the control experiment for galaxy formation. In the crowded environments of clusters and groups, a galaxy's evolution is dominated by external factors: close encounters with neighbors, the pressure of hot intracluster gas, and the relentless tidal forces of the larger halo. These processes, known as environmental effects, constantly harass and reshape galaxies, making it incredibly difficult to isolate the fundamental physics of how a galaxy forms from the simple collapse of gas within a dark matter halo. But a galaxy living in a void is blissfully free from this cosmic noise. It evolves in near-total isolation, its fate determined almost exclusively by its own internal processes: the efficiency of its star formation, the feedback from its supernova, and the activity of its central black hole. By studying the galaxies that form in these void halos, we can finally see what a galaxy looks like when it's left to its own devices, providing a pristine view of the basic relationship between a dark matter halo and its luminous galaxy. When astronomers do find these rare void galaxies, they often appear strange and anachronistic. Many of them are low-mass, gas-rich, and have a bluish tint, indicating they are still actively forming stars, much like galaxies in the early universe. While their counterparts in denser environments have long since had their gas stripped away or used up, transforming into red and dead elliptical galaxies, the void galaxies have been left behind, evolving at a leisurely pace. They are cosmic living fossils, offering a glimpse into a more primitive and quieter era of galactic evolution. Their dark matter halos, in turn, are predicted to be more relaxed and spherically symmetrical, lacking the distortions imparted by major mergers. They may also possess a different density profile, perhaps with shallower inner cusps, since the lack of violent merger events and the weaker overall gravitational potential could result in a gentler collapse. Observing these subtle differences in the halos themselves is incredibly challenging, but even studying the properties of the galaxies they host gives us indirect yet powerful insights into the nature of the invisible foundations upon which they are built. The very existence of halos in the deepest voids also serves as a stringent test for our cosmological models, particularly for alternative dark matter candidates like warm dark matter. Recall that warm dark matter suppresses the formation of structure on small scales. Since void halos are the smallest, faintest, and most fragile structures to form in the universe, they would be the first to be wiped out if dark matter had too much thermal motion. Therefore, finding a population of small, dark matter-dominated dwarf galaxies floating in the profound emptiness of a giant void would place a very tight constraint on how warm dark matter can be. It would tell us that the particle must be cold enough to allow these faint ripples to collapse even in the most unfavorable environments. Conversely, if deep surveys of voids turn out to be even emptier than our current predictions, it could be a tantalizing hint that dark matter does indeed have a warmer nature, smoothing out the universe on the very smallest scales. The profound silence of the cosmic voids may, paradoxically, be shouting to us the fundamental properties of the universe's most elusive substance. Projecting our gaze across trillions of years into the future, we confront a cosmic destiny that is both grand and profoundly isolating, a fate dictated not by the pull of gravity but by the relentless push of an unknown force. To understand the future of dark matter halos, we must first grapple with the ultimate driver of cosmic evolution, dark energy. This mysterious component, which makes up about 70% of the universe's energy budget, acts as a kind of anti-gravity, causing the expansion of space itself to accelerate. For the past several billion years, this acceleration has been a background hum. But as we look forward, its influence will grow from a whisper to a roar, fundamentally reshaping the entire architecture of the cosmos and the halos that hold it together. In the near-term cosmic future, on scales of tens of billions of years, the story is one of consolidation and merger. Our local group of galaxies, dominated by the Milky Way and Andromeda, is destined for a collision. Drawn together by their mutual gravitational pull, these two spiral giants will merge into a single, larger elliptical galaxy, often dubbed Milky Way. During this monumental event, their dark matter halos will also merge. Unlike the stars and gas, which will be violently rearranged, the dark matter particles will simply pass through one another, their halos overlapping and blending into a new, more massive, and likely more spherical halo. This process will be repeated across the universe in other galaxy groups as gravity continues to work locally, binding nearby structures together even as the global expansion accelerates. For a time, the universe will be a place of these isolated island universes, each a massive galaxy formed from countless mergers, embedded within a correspondingly vast dark matter halo. But this era of consolidation is only a temporary phase. The accelerating expansion driven by dark energy will eventually overwhelm even the strongest local gravitational bonds. As space stretches at an ever-increasing rate, the space between these isolated galaxy clusters will grow at speeds that effectively become superluminal. Any galaxy or cluster not already gravitationally bound to our own will be pushed away by the expanding fabric of space, eventually disappearing beyond our cosmic horizon. The universe will become a collection of increasingly isolated islands, each drifting apart into an ever-deepening darkness, unable to see or interact with any of the others. For a civilization living within Milky Way trillions of years from now, the observable universe will have shrunk to only their immediate galactic neighborhood. The rest of the cosmos will have vanished, leaving behind an empty black void. Within these final, isolated halos, a slow but inevitable process of evaporation may begin. Even though a dark matter halo is a gravitationally bound structure, it is not a perfectly static one. The particles within it are in constant motion, orbiting the common center of mass. Each particle has a specific energy and velocity. Statistically, there is always a chance that a particle on a very elongated orbit, or one that receives a slight gravitational kick from a passing star or another dark matter particle, could gain enough energy to reach escape velocity. In a static universe, this process, known as violent relaxation and evaporation, would take an unimaginably long time to have any significant effect. However, in a universe dominated by dark energy, the gravitational potential well of the halo itself might be subtly altered. As the halo becomes more and more isolated and the background density of the universe drops to near nothing, the effective edge of the halo could become less distinct, potentially making it marginally easier for particles to drift away over cosmological timescales. This would not be a dramatic dissolution, but a slow, barely perceptible leak, a gradual fading of the gravitational foundation over eons that dwarf the current age of the universe. This leads to a profound and haunting question: could dark matter halos be eternal? If dark matter is truly collisionless and non-annihilating, and if the evaporation process is infinitesimally slow, then the answer might be yes. Long after the last stars have burned out, after the black holes have evaporated via Hawking radiation, and after the protons of normal matter have decayed, the dark matter halos could remain. They would be the last structures standing, eternal cosmic landmarks in an otherwise featureless and frigid void. They would be fossils of a vibrant past, their distribution and shapes preserving a record of the initial conditions of the Big Bang long after every other trace of that event has faded away. In this ultimate future, the universe would be dark, cold, and empty, save for these vast, invisible ghosts silently tracing the outlines of a universe that once was. Yet, this eternity is not guaranteed. Our understanding of dark energy is still in its infancy. The simplest model treats it as a constant force, Einstein's cosmological constant. But if dark energy is instead a dynamic field that could decay or change its properties over time, the entire cosmic fate could be rewritten. A future phase transition in the dark energy field could, in principle, shut off the acceleration or even reverse it, leading to a big crunch where the universe collapses back on itself. In such a scenario, the dark matter halos would not evaporate. They would be drawn together in a final, catastrophic merging event, culminating in a singularity. Alternatively, if dark energy strengthens over time, leading to a big rip, even the tightly bound particles within a dark matter halo could be torn apart as the expansion of space accelerates to infinity, ripping the very fabric of reality and dissolving the halos in a final instant. The ultimate fate of these invisible scaffolds is therefore inextricably linked to the deepest mystery of all, the true nature of the dark energy that now governs the cosmos. Their future is a story yet to be written, a final chapter that depends on physics we have only just begun to imagine. And so we arrive at our final and perhaps most profound mystery. After this grand tour of 24 enigmas, from the ghostly plains of satellites to the silent search for annihilation, we are forced to take a step back and ask a question that strikes at the very foundation of our quest. Are we even asking the right questions? Every puzzle we've encountered, the cusp core problem, the missing satellites, the unexpected galactic giants seen by the James Webb Telescope, has been approached with a shared underlying assumption that dark matter is a particle and that Einstein's theory of gravity, while needing a cosmological constant to explain cosmic acceleration, is correct on galactic scales. But what if this entire framework, the very lens through which we view the cosmos, is the source of our confusion? What if these aren't puzzles to be solved within the current paradigm, but are instead glaring signposts pointing toward a need for a revolution in physics itself? This line of thinking leads us to the most radical alternative on the table, that dark matter doesn't exist at all. The proposal, known as modified Newtonian dynamics, or MUND, suggests that we don't need to invent a new, invisible substance to explain the universe. Instead, we need to modify our understanding of gravity itself. The core idea is that on the incredibly low accelerations found at the edges of galaxies, where the gravitational pull is billions of times weaker than on Earth, gravity stops following Newton's inverse square law and becomes stronger. This modified force law would naturally explain why stars on the outskirts of galaxies orbit so quickly without requiring any extra mass. It's an elegant solution in its simplicity, replacing a universe filled with an unknown particle with a single adjustment to a fundamental law. And indeed, MUND has had some remarkable successes. It can predict the rotation curves of many individual galaxies with stunning accuracy, often better than the dark matter model can without extensive and fine-tuned computer simulations. For its proponents, this is a clear sign that we are on the wrong track with dark matter, that we are constantly trying to fix a broken model by adding ever more complex and invisible components. They argue that we are like the ancient astronomers who added increasingly elaborate epicycles to the Ptolemaic model of the solar system to explain the planet's motions, refusing to accept the simpler heliocentric truth. From this perspective, dark matter is the modern equivalent of those epicycles, a cumbersome fix for a fundamentally flawed theory. However, the dark matter paradigm has not endured for decades without powerful reasons. While MUND excels at explaining the dynamics of individual galaxies, it faces immense challenges when confronted with the larger-scale architecture of the universe. The most damning evidence comes from observations of colliding galaxy clusters like the Bullet cluster. As we discussed, the gravitational lensing map shows that the majority of the mass is clearly separated from the visible matter. MUND struggles mightily to explain this, as its modification to gravity is tied to the distribution of visible mass. How can a modified gravity law create a strong gravitational field where there is very little visible matter to source it? This observation alone is, for many scientists, a near-fatal blow to MUND, powerfully suggesting that the mass really is located in a separate, invisible component. Furthermore, the lambda-cold dark matter model provides a breathtakingly successful description of the universe as a whole. It accurately predicts the detailed patterns in the cosmic microwave background, the large-scale distribution of galaxies, and the very fact that galaxies could form in the time available after the Big Bang. MND, in its original form, does not have this cosmological scope. It was designed for galaxies, and integrating it into a full theory of the universe has proven incredibly difficult. Some theorists have attempted to create relativistic versions of MND, known as tensor vector scalar gravity, but these theories often become even more complex and introduce their own set of problems without matching the comprehensive success of the standard cosmological model. This leaves us at a fascinating and deeply uncertain crossroads. The failure of MND to explain key pieces of evidence like the bullet cluster is significant, but the persistent small-scale failures of the standard dark matter model are equally troubling. This has led to a growing sense that the truth may lie in a more complex third option. Perhaps dark matter is real, but it is not the simple, cold, and collisionless particle we have long assumed. The mysteries we've catalogued could be hints that the dark sector is rich and complex, with multiple types of particles and forces that interact in ways we haven't yet imagined. This would explain why the pure gravitational predictions of cold dark matter work so well on large scales, while failing to capture the intricate details of individual galaxy formation. Alternatively, we may be witnessing the limitations of both approaches, signaling the need for a paradigm shift so profound that it transcends the current debate. Could it be that both dark matter and modified gravity are approximations of a deeper, more fundamental theory that unifies gravity with quantum mechanics? The true nature of space-time and mass on cosmic scales may be something we have not yet even begun to conceptualize. The fact that our two best theories, each with its own compelling successes and glaring failures, are so fundamentally incompatible suggests that we are grappling with a problem that requires a new way of thinking altogether. The 25 mysteries of the cosmic dark matter halo are not just a list of unanswered questions. They are a collection of clues left by a universe that is far stranger and more wonderful than our current textbooks can describe. Our journey to understand the invisible architecture of the cosmos has not reached a conclusion, but has instead opened a doorway to a future physics waiting to be discovered. And so our journey through the shadows of the cosmos draws to a close, but the investigation is far from over. From the fundamental question of dark matter's very identity to the ultimate fate of its halos in a dark energy-dominated universe, each of these 25 mysteries represents a fracture in our understanding, a place where the universe whispers that there is more to learn. We have seen how the cusp core problem and the too-big-to-fail galaxies challenge the very blueprints of our simulations, while the precise planes of satellites suggest an order to the chaos that we cannot yet explain. The ghostly ultra-diffuse galaxies and the potential existence of pure dark halos show us the startling diversity of cosmic structures, and the Hubble tension threatens to unravel our entire cosmological model. The hunt for annihilation signals has returned a profound silence, pushing us toward more exotic particles, and the violent collisions of galaxy clusters have given us our most compelling, yet still indirect, evidence. Every strange rotation curve, every anisotropic stream of stars, and every unexpected giant galaxy in the early universe is a piece of a puzzle so vast we have not yet even assembled its edges. What makes this pursuit so exhilarating is that these are not merely technical problems for specialists. They are fundamental questions about the nature of reality, the fabric of space-time, and the composition of the universe we call home. The dark matter halo is not a distant abstraction. It is the invisible architecture of our own galaxy, the gravitational anchor for our solar system's journey through the Milky Way. To unravel its secrets is to understand the very stage upon which our existence plays out. The fact that after decades of dedicated searching, the true nature of over 80% of the matter in the universe still eludes us is not a failure of science, but a testament to the profound depth and mystery of the cosmos. It is a humbling reminder that our perception is limited and that the universe is filled with wonders beyond the light our eyes can see. Now we turn the question over to you. As you look up at the night sky, which of these 25 mysteries captures your imagination the most? Does the eerie coherence of the satellite planes, looking like a cosmic conspiracy, spark your curiosity? Or are you drawn to the philosophical standoff between particle dark matter and a modification of gravity itself, a debate that could redefine the laws of physics? Perhaps the sheer scale of the unknown, embodied by the silent search for annihilation or the ghostly presence of ultra-diffuse galaxies, fills you with a sense of wonder. The exploration continues with new telescopes and more powerful simulations coming online every year, each one offering a fresh chance to peer into the dark. So stay curious, keep looking up, and remember that the greatest story ever told, the story of our universe, is still being written, with its most crucial chapters hidden in the